Right. So, and then we were asked to give you some updates. The break is at 2:50. So if I'm just talking, everyone just tell me break time in case I lose track. There are on-site volunteering opportunities for PyCon, swag bagging from 4 to 8 p.m. I think you just show up and put stuff in bags. They need help at the registration desk. And there's a web page, there's 2 web pages that have information about volunteering for PyCon. In case you want to write that down. Okay. And then we have the prerequisites. And then we go with the relational database review. So what I should do is get an idea of people's Python experience level using Python for less than a year. Okay, we're using Python between 1 and 3 years, between 3 and 5 years. Okay, over 5 years. So we see that's how it goes. We have every demographic represented. So I am absolutely positively sure to let someone down because it'll either be too easy or too hard. So assuming someone's going to blog how the talk was either too easy or too hard, if you like the talk, blog about that also. So there's a counterpoint to the guy who's going to complain that it was too easy or too hard. Are there any questions from the people that did the handout, like about some of the relational database stuff? Did I get anything wrong? Or, you know, we're all good with what was in the handout. We covered tables and columns and data definition language, DDL, and inserts and updates and deletes, and then we're all pretty cool with the general idea and selects. Am I going too fast? Joins. Grouping, we're not really going to do grouping in this thing. Well, there's a little bit of grouping. It's not that critical for this tutorial. Overview of ACID, atomicity, ISO, and then there. Great. Okay, and also who has used SQLAlchemy before? Like, okay, who actually uses it for work and actually deals with it every day and wants to just learn more about its basic fundamentals? Who's absolutely no idea SQLAlchemy? Okay, who uses Django ORM? Maybe. Okay, all right. So it seems like most people here have used some kind of relational database abstraction layer, and you're okay. That'll help. So SQLAlchemy is the database toolkit for Python. That's our tagline. It was introduced in 2005, and it presents an end-to-end system for working with the Python DB API, and I'll show you what that is in a little bit, and relational databases and the SQL language. And the current release is 0.8.0, which I just put out this weekend. And we're very close to where I'm going to call it 1.0. I'm not totally sure yet, but I might just go from 0.8 and just kind of jump to 1.0 kind of quickly, because it really is kind of time to be 1.0. It's only been 7 years or whatever. So the goals of SQLAlchemy, it's to provide code helpers, tools, components, APIs, what have you, to assist with the database development at every level. Provides a consistent facade over the Python database API. Provides an industrial strength but optional object relational mapper, or ORM. And it can act as the foundation for any number of third-party or in-house tools. If you do a search on PyPy for SQLAlchemy, obviously there's dozens of packages that are built on top of SQLAlchemy to provide different kinds of relational patterns and fun things. We're going fast, actually. Okay. So philosophies of SQLAlchemy. The philosophy of SQLAlchemy is bring the usage of different databases and adapters, database DB APIs, to as consistent of an interface as possible. So basically, all the world of databases, we have MySQL and Postgres and SQLite and Oracle and Sybase and Microsoft SQL Server and Informix and DB2 and everything else. They every single one of them has completely different stuff going on. Like they all have the select star from table. Everyone's got that, but they are so different in so many ways. And SQLAlchemy is still going to expose those distinct features and behaviors, but it's going to try to find this middle ground between where we can kind of have some consistency between these platforms, but at the same time not lose the ability to take advantage of what each platform offers, which is a tricky thing, because usually, historically, database abstraction and ORMs, when you do that, a kind of an old-fashioned approach is to kind of distill each database backend down to its, the lowest common denominator of all those backends. So if they all can do a select, then that's all that your thing can do. And if Postgres has, window functions, but SQLite doesn't, well, your ORM won't have window functions. Things like that. So SQLAlchemy is trying. Everything about SQLAlchemy is kind of a middle ground. There's nothing. We're not all anything. We're middle ground all the way. Just try to walk that line between where we don't want to write completely different code for every database, but we want to still be able to do some things that are database specific. And it actually has a lot of techniques nowadays to really, like if two different databases do something totally differently, you can write your own little adapter that does the thing you need to do for both backends, and it'll look pretty transparent. So it's pretty cool for automating the work of talking to a relational database. It's a tool for automation. So it never hides the database or its concepts. Developers have to continue to know and think in SQL. The best way to write a SQLAlchemy query is to just know what the SQL query in your head would be, and you pretty much can write it in SQLAlchemy's language fairly straightforward once you're good at it. But instead of trying to hide anything, it just provides automation of the concept of talking to the database and DRI, which is don't repeat yourself. So the concept of don't repeat yourself, I like to say that a good application is maybe 80% dry, meaning if you have an application that's 100% dry, like nothing is repeated anywhere, it tends to be really rigid. Like if you need to add something new to your app, everything doesn't fit into your big giant system. So I say 80% dry, so there's a little bit of wiggle room for things. You don't quite. There's a little bit of repetition here and there, so that there's some flexibility. So SQLAlchemy is designed to help you to write the best database interaction layer that you can for your application. So it's really it's not a casual dip in the pool. It's kind of you need to get into what its philosophy is the best way to work with it. Allows expression of database and SQL tasks using declarative patterns. That's more of the ORM, and we'll see what that looks like after the break, actually, which will be the ORM. So I should say basically the way we're going to. Well, I'll show that in a second. This is an overview of SQLAlchemy. This picture is on the website. If you go to the documentation, there's an introduction page, and this is the same picture we've been showing for years. This is kind of a overall architectural view of what SQLAlchemy is. So, you start with your database. The cylinder symbol is the universal symbol for database. And then when you have your Python installed running on your SQLite library running, that's called the Python Database API, like PsychoPG2 for Postgres is a DB API, MySQL for Python. So we're not at SQLAlchemy yet. Then you go here. OK, so SQLAlchemy has this first layer called the dialect, which is code that knows the special things about your database API and the special things about your database. Connection pooling is kind of an optional but usually used feature that will maintain some connections so you can reconnect really quickly. And then those are revealed through an object called the engine, which we're going to see in a minute. So the engine is the most core unit of connecting to a database with SQLAlchemy. And then along with the engine are these components of the SQL expression language, which we're going to do as a whole section, and the schema representation library, which is also a whole section. And then all of that is part of a big thing called the SQLAlchemy Core. And none of this has anything to do with object relational mapping whatsoever. So when you say using the SQLAlchemy, you could be totally here, and you're not using an ORM at all. You're using just the SQLAlchemy Core. And that's what a lot of people use. If you go to Reddit, Reddit uses their really super custom thing built on Core. Now, ORM is a whole other thing. It's a whole topic of its own, and that builds on top of the Core. So the ORM doesn't talk to the database directly. It goes through SQLAlchemy's Core APIs to do what it does. Any curiosity questions so far? Or any? OK. Well, what I can do. Well, actually, this one out here. I'll show you this slide, but most of the slides are not really going to be that low. Most of the stuff will be in the slide runner, so we shouldn't have too much of a problem. That's the bottom, if you can see it. Don't worry, we're not going to be in the slides for most of the thing. Some of it. So the core, here's the rundown I just basically gave. The engine is a registry which provides connectivity to a particular database server. The reason it's a registry means it's kind of this object in a computer or an application that just stores some common repository of information about something. In this case, the engine stores information about the database that it's just connected to. The dialect is kind of this thing you don't see directly usually. It's within the engine. It interprets generic SQL and database commands in terms of a specific database API and the database backend, so it knows how to produce a query that MySQL will like versus a query that Oracle will like. Connection pool holds the connection of database connections in memory for fast reuse. And there was recently a big flame war on Hacker News about PG Bouncer and how connection pools are terrible. But I still think they're fairly handy for general use. The SQL expression language allows SQL statements to be written using Python expressions, and we'll see a lot of that. And then the schema and type system uses Python objects to represent tables, columns, and data types. So that's what's in the core. And the ORM, what's the job of the ORM? The ORM allows construction of Python objects which can be mapped to relational database tables. We'll see a lot of that. It can transparently persist objects into like the state of a Python object, into a database table using a pattern called the unit of work pattern. And that's all coming up. It provides a query system which loads objects and attributes using SQL generated from those mappings. And it builds on top of the core. So all the SQL that the ORM generates is generated via the core. And this diagram I actually got from someone else. This is plagiarism. A guy that ran a tutorial for PyOhio had this idea that SQLAlchemy is like an onion. And I thought that was a great idea. Because it really is like this, that you start, and the way when I wrote SQLAlchemy, I started this way. First I wrote this engine thing that knew how to emit SQL with the Python database API in a way that I liked. And then I wrote the system that talks about how tables in a database can be defined in Python objects. Then I wrote SQL expressions, and then object relational mapping was kind of on top of all that. So it's like an onion, and you can learn it from the inside out or the outside in. And I've kind of flip-flopped over the years as to should I teach the ORM first and show some quick success and then get into how it works later, or the other way from the inside. So this particular talk, which I had in the intro on the website, so I'm sure you saw it, we're going to go from the inside out, which I think will be better because the engine stuff should be pretty simple. The metadata stuff should be fairly enlightening. The SQL expression stuff we're going to take until the break. And then no matter how far or not far we get by the break, after the break we'll do all object relational mapping after the break. Because really, when you use SQLAlchemy, we're normally using the ORM all the time, but we know about these other things. We know about these other concepts at the same time. The most confused users that I get on the mailing list are those who know the ORM, they know what it's doing, but they have no idea what an engine is. Those are the people who need, now they can learn new ORM patterns, but I have a really hard time explaining to them, well, there's this engine and it's kind of in the middle because they don't have that concept. So I'd like to get the concept across. And then as far as learning how to do fancy ORM stuff, hopefully you can go forth and, get more stuff. So this is the basic stuff. So there's also a color. I like to use color coding. So we have green, assuming everyone can see those colors as distinct, because some people can't see color. Green, blue, and orange, and red. So we'll see. So we start with level green, which is the engine, and right on time. So so with the engine, we start with what the engine, the job of the engine is to deal with this thing called the Python database API, and that is a Python PEP. You guys know what a PEP is, a Python enhancement proposal. So basically everything that Python does, anytime they want to add a new feature, they make this thing called a PEP. And there's a whole website of all the PEPs. And basically all the features come out as all the APIs, and the WSGI API and the style guide are all PEPs. So PEP 249 is the Python database API. And it's the de facto system for providing Python database interfaces. There are a few packages for talking to database that don't use the DB API, but they are few and far between. There are many DB API implementations available, and most databases have more than one. For MySQL, there's at least 7 or 8 DB APIs you can use. And then the features and the performance and the stability and the quirks and maintenance and everything varies wildly. DB APIs for as good a job as PEP 249 attempts to do to define consistent behavior, it has a lot of like, this is suggested, and it's suggested that APIs do this, and most APIs will want, it doesn't say, you shall do this, you shall do that. It's kind of like, yeah, you can do this, you know, it's probably a good idea to do this. So what happens is all the DB APIs all have their own little quirky things. You know, there are, most annoyingly, 6 different formats for using bound parameters, which is really annoying because you only need 2. So what this code is, and I know that how far can people see almost to the bottom? You don't have to see the whole thing. It's just if you can see maybe to this part, you'll get the nutshell. So when you work, so this is an example of code using a database API known as PsychoPG2, which is an adapter for the Postgres database. And this is what it looks like. You make a connection. You connect, give it a username, password, and some information about where your database is, maybe a host name, which is not here. And then when you want to actually do something with results, you need to make a cursor. You say connection.cursor, and then we can use the cursor to execute some SQL. So we're doing a select from a table here. And that little emp ID symbol is a bound parameter, which means it's going to replace that number 5 into the statement. But we let the driver do that because different databases have different ways of substituting parameters. And a lot of you have probably heard about something called SQL injection attacks, which is when you see this a lot in like PHP applications where they'll write a SQL statement where it's like you're logging into a website and it'll be like select star from user table where password equals, and it'll be like quotes and a string concatenation. And then someone will go onto the website and type a bunch of SQL in the password box with some semicolons so that they will inject a whole new statement into the statement and then delete the guy's user table, something like that. So that's SQL, and there's a lot of websites being hacked, and it's always through this program called WordPress. So because they don't have a consistent pattern. So we want to use this bound parameter thing, and it really is this whole, I feel like it's a whole subject because people always don't seem to know it fully. Postgres actually is going to substitute that number 5 into the string and make sure it's properly quoted, and then it'll send it to the database. But if you talk to a database like Oracle and use a database API called CX Oracle, it actually never does the interpolation at all in Python. It all gets sent back to the server, and the Oracle server actually deals with the separate parameters. So you can't assume you know where that number 5 is going to go. So we keep it separate, and it's not just about string formatting. It's also about interpreting different data types like dates or booleans or large decimal values in the way that the backend wants. So when we talk to a relational database, we want to, as much as is humanly possible, to substitute all literal values, numbers, names, dates, any kind of nouns that represent data in the database. Not the structure of the statement, not the names of columns, not the names of tables, but the data that might be inside of a column or in an expression. We always want to have that escaped out. So when we use SQLAlchemy, it's going to make it actually kind of difficult to not do that. One of the big things SQLAlchemy will give you is you almost never have to worry about making sure literals are bound parameters. Checking my time, good. So the DB API I thought was a little bit verbose that first you connect, but you can't just execute from the connection. You have to make a cursor. And then the cursor represents where you get the results from. And that is the traditional database approach. I thought it was a little bit verbose. So the engine's going to try to make this a little less verbose. So important facts about the database API is that when we just saw that connection just now, this is the one area that the DB API's PEP 249 is fairly strict, is that the connection must be in a transaction. So if you connect to a database with DB API and you start running insert, update, delete statements, by definition, they will not be committed to the database until you call the commit method on the connection. And that is basically the opposite of what we call auto-commit. It's basically not auto-commit. It's always the pending thing. The only exception to that is if you're using MySQL with the MyISAM database engine, which doesn't have transactions. So as providing the database you have, which almost all of them support transactions, you will not be in auto-commit by default. And database API, a lot of them do have an auto-commit mode, but it's not a standard part of the spec. So SQLAlchemy does not build upon a database API level auto commit, it actually has its own auto commit, which we actually don't even use that often. So I'll show you that later. So as I just went through, the DB API encourages bound parameters via the execute and execute many methods, but it has 6 different actual string formats for that string I showed you. There's other formats that we'll have to deal with before we actually use SQLAlchemy. All DB APIs have inconsistencies regarding data types, primary key generation, custom database features, result cursor behavior, all kinds of stuff. It's really more varied than anyone could imagine. And I know there's a bullet that's too low for people, but won't be too many. DB API has its own exception hierarchy, which SQLAlchemy exposes directly. Meaning if you try to connect with database API and the connection fails, it'll throw interface error or something like that. And if you try to do a statement that inserts a row with the same primary key, you'll get a integrity error. And these are errors that are defined by the database API. SQLAlchemy has its own version of those exceptions that it will wrap. And I don't want to go too far into that detail because it's kind of a minutiae detail. I don't know why I put it in the slide, but it's something to know. So SQLAlchemy, so far we're just doing the Python database. We're doing other things that already exist before SQLAlchemy. So the first layer in SQLAlchemy is known as the engine, which is the object that maintains the classical DB API interaction. The thing I just showed you was the classical DB API interaction. And with that, I would show you this. I would go to the first Python scripty thing, which means that for those of you who managed to get the thing installed, we would run the slide REPL command. Who's got slide REPL going? How many people have it going? Okay. So we do have some helpers if people want to. Is Ben? You're here, and Ben. Yeah. So if people want, does anybody want help while we're talking to get the slide installer? Anyone who doesn't? Okay. We have helpers in the back, and raise your hand, and they'll come by and try to help. So I'm going to run it with this flag -- pres, which will make it clear the screen, and you can do that too if you want. And if you don't run with the -- pres flag, it will just kind of roll down the screen, which might be easier for you to scroll up and see what's happened. So, and then I just started up, and the first thing it did, I didn't really start it yet. It ran a bunch of SQL just to kind of set up the very quick examples we're going to do for the engine. So the first slide is actually this. So here's the first slide. So, right, okay. So this is legible. The letters are big enough, and okay. So this is what it looks like. So now we're in Python, and we're going to actually do something with SQLAlchemy. We're going to create an engine. And it's the function we use is aptly called create engine. So we import the function, and then we say engine equals create engine, and then we pass it a URL. I'll show you some examples. And so what this URL is doing is it's creating a SQLite database called sum.db. It's creating it in the local file system. If we wanted to make a SQLite database at an absolute path, we would actually use 4/. That's how it would look. Just kind of a historical detail. If we wanted to connect to Postgres, the URL would look more like this. If I could type. This is the URL I type every day when people email me Postgres questions. I have this little test database that I use. So the normal format is the first part of the URL is kind of this keyword that identifies the kind of database you're going to talk to, and there's a default dialect. If you wanted to specifically talk with the PsychoPG2 database API, which is the default, you could say that. You could say that, Postgres for PsychoPG2. Then you have username, :password, @hostname / database name. Only SQLite, which doesn't use a host. SQLite it uses just local files. It doesn't use a server. So you just give it a file name. So SQLite is what we're doing here because most people here have SQLite installed as part of your Python build, and it's pretty easy to work with for demonstration purposes. So we have this engine object. And there it is, all right? And it's a Python object. It hasn't actually connected to the database. All it knows is this URL we've given it, and it won't do anything until we tell it to run some SQL or to connect. And then it'll suddenly be like, oh, I got to go to this URL somewhere. I got to figure out what I'm going to do. So the next slide should show that. So this next slide is just showing the most handy convenience method of the engine is just a method called execute, where you pass it a string, And that string goes straight to the database API, as is. This is probably not, you probably don't remember this, but when I showed the DB API example with CycloPG2 earlier, there was a bound parameter which used the Python format with the %sign in parentheses and an S, and now this SQLite uses the :name format. Because we're not at the level yet where SQLAlchemy is trying to help us with the bound parameters. This is just the low level, the engine's going to run a statement through the database API. And so you see I have this handy press return to run code. That's self-explanatory. It basically hasn't run the code yet, so it's not fetched. And if we look at the row, we just, like Reaper row, it looks like a tuple. It also acts like a dictionary. Is that too low on the screen? Can people see what just happened? Because it went kind of low. I can make the screen a little higher. It doesn't really need to be that low. So you can say row, and you can hand it, emp ID. It'll give you that. And then you can say row.emp ID. It'll give you the same thing. So it's kind of trying to be convenient, kind of like a, I'll give you the data as much as I can tell what you're asking for. When you get all the rows from a result, it closes itself automatically, which means it's going to release the DB API cursor underneath, and it'll release the connection that we have back to the connection pool. That will usually happen automatically. You can always say result.close if you want to. And if I say result fetch 1 at this point, it should give me an error. Yeah, because it says this result object is closed. So the result object is kind of like this active handle to a list of rows you got back from a SQL statement. So a result object can be iterated. So in Python, iteration means like for something in iterator, it'll naturally give you the rows back. So here we have select star from employee, and that's all the data in this little sample table I've created. Ed, Jack, Fred, primary keys. I can say fetch all, which will give me a list of all the rows. So same thing, but I can just get a list with the row object inside of it. Now, that's selecting. Does that make, that's pretty simple, right? Yeah.
Quick question. Can you get the data out of a single row in the form of a dictionary?
Yes, because actually what we just, here, let me try to, I could actually do that. If I get out of here, I can go this, and I can go to slide 8. I should be able to say, if I say that, and I say row equals result fetch 1. First of all, the row is kind of like a dictionary. So it really will act. There's the keys, and you really it acts enough like a dictionary that if you did say dict row, it should give you but it pretty much acts like a dictionary anyway, with extra stuff. Yeah. So if you really want it to be completely dictionary, you could just say dict row and you'll get that. So yeah, it's pretty dictionary-like. So that's selecting, and this is at the engine level, which in reality, we normally don't really use SQLAlchemy at this level too often, except we're just testing something. So when you do a statement like an insert, or an update statement, or a delete statement, SQLAlchemy will do something called auto commit. Because remember, the DB API it doesn't auto commit by default. Everything you do is in this transaction that stays there until you commit. So what we're doing here is we have this engine, which this will become clear as we go, has this connection pool. It's not really a connection. It's actually a pool of potential connections. So when you say the engines, tell it to execute a statement, it'll say, oh, let me connect to the database. Let me run your statement. Let me give you your results. And then let me close the connection and close it, or either put it back in the connection pool or close it fully. In the case that you ran a statement like an insert or an update or a delete or other statements with certain rules attached, it will also commit the transaction automatically because we didn't tell the engine that we want any kind of transactional scope. So in this case, you'll see it hang. My slide runner's hanging. Wow. This is so embarrassing. Okay. That's how we do that. It might be because let's do it the old-fashioned way. All right. Anyway, that didn't happen. So we ran the insert statement. So we insert a row into a table. And then you see in the SQL log, see, when you work with SQLAlchemy, especially in the beginning, it's all about watching the SQL it's doing. It's about getting to know what it's going to do based on what you told it. So when you run an insert or an update or delete at this level, it says, oh, well, because you didn't tell me about a transaction, I'm also going to commit it for you. It does auto commit. When you put strings in like this, it actually is parsing the string for the word insert, and normally that's not how it works. This is all exception case stuff. So that's how it works. That's how SQLAlchemy's auto commit works. And then you get a result back, which actually is the same kind of result you get from a select, except this result doesn't have any rows in it. It's actually closed already. I can't show it to you because we just lost it there, but it's closed. So it auto-closes from an insert. Insert is auto-commit, updates auto-commit, deletes auto-commit. If I want to do more than one thing with a certain connection, like because I remember the engine is going to connect to the database, do some stuff, and then close the connection, which might be in a pool or it might not be. If you want to actually connect and have this connection that represents this one connection and do 10 things on it, you can say connection equals engine.connect, and that will give you this connection object that you can actually do the same methods on, like execute. Con is a connection object. It's now closed, so I can't run things on it, but it just represents explicitly checking out a connection from the pool or making a new connection. You can do stuff on it, and then when you close it, it's more like a traditional connect and close pattern, which sometimes is more appropriate at this level. And then one more level up from that is if you actually want to run a transaction, I mean, you want to do several statements within a begin and a commit that you can roll back all at once. You can do that too with a connection. So and the reason we need to have the connection when we do the transaction in the normal case is that the transaction is something that happens on one connection at a time. You can't, if you connect it to the database 3 times, you normally, it's a two-phase commit, but let's just not without that. If you have 3 connections, you can't have one transaction that's on all 3 connections under normal circumstances unless you're using some more advanced features. Typically, a transaction is something that is only in the scope of a single connection to the database, and then you and really, when you connect to a database, that's often called a database session. And then within the session, you can have multiple transactions, but only one at a time. So what we're doing here is we're pulling a connection from the database, from the engine, saying to the connection, hey, can you begin a transaction for us? Sure. We get this object back called the transaction. Then we can run a few statements that do something. And then we say transaction.commit to commit the transaction. If we didn't want to commit, we could say transaction.rollback. And then to be all finished with it, we say connection.close. So you'll get those 2 statements within a begin and commit pair. And then a more shorthand version, which I'm sure you'll all appreciate, is to use a context manager. So this is so we start with the engine. We say with engine.begin as connection. And then it'll run those statements on the connection for us. And it'll all do it within a transaction and close the connection and do it all really nicely. So that is the last part of the engine chapter. And then we have a short exercise, which is pretty much to just type what we just did. But does everyone, yeah.
If you're using the with statement there,
Yep.
is there a way to roll back?
You would throw an exception. Because the with statement is basically meant like you're expecting it to succeed. If an exception is thrown, it rolls it back. Yeah. So the first exercise, now this is where if you have the slide runner going, it's handy because you can just type it in your little slide runner. Now in past tutorials, I don't know if I've done too many exercises, so I've got to learn the etiquette of exercises. So I guess I would give you like a minute because it's not too hard, and then I'll start typing it. Does that work for people? Are people doing the exercise already, or basically that table is already in the database. Insert a row, and then select all the rows back. So I see, okay, people are typing. That's good. That's good. And this is where some people will be like, this is really too easy. Or some people would say this is really too hard. He went too fast. No one's, okay, I'm looking for those nods like, yeah, too hard. Nah, too easy. Okay, and then 2 to 220 will be schema. Yeah, SQLite. Yeah. I mean, this one you could just scroll up, and But it's the practice. You know what it is? It's when you actually have to get to type it yourself. You kind of, I don't know. You kind of, yeah, it gets a little more. Yeah. Should I start typing, or am I giving it away? If I get to the end, then you didn't. All right. Any success yet? One? You got a trace back. That's good. Yeah, yeah. Now if somebody wants to use, you can also, if it might be hard to type into the REPL. If you want to use a text editor and run the script, you could do that too. I mean, I figured it's easier for people to just go in the thing and. Hey.
So if the database doesn't exist, like you say, it doesn't connect right away when you start at the engine.
Mm-hmm.
So it'll fail later on when you actually try to run something, or can you do them before something like?
You can just say engine.connect.
Okay.
Yeah. Everything about it, a lot of the libraries, the ORM, everything is lazy initializing.
Yeah.
So that's, yeah.
Okay. So you can do it up at the ORM level too.
Yeah, the ORM, when you start using the ORM session, we'll show you, it doesn't do anything until you tell it to push. So you can make objects and there's no database connectivity at all. So you won't, so yeah, some people are thrown off by that it won't, you don't know that your connection doesn't work until like there. In practice, it's not that big a deal. You just got to stack trace. But yeah, if you want to do a connect up front, you can do that. All right, so I'm going to, it works. Okay, great. So if you said this, you get your Dilbert. Did people get the select happening yet, or? Okay, I'm going to do that. I'm just watching people who are looking up or not. So I'll do the next part because we'll go to the next thing. And result fetch. There you go. Here's your table. Was this hard or easy, or was it just hard to type it on the REPL, or any instant feedback for no complaints? This is the easiest exercise that we have. So yeah. Okay, well, you could do it that way. You could say, you could totally do this. You could say plus, you could say this just like old school. I can't even do it. The string, like yeah. Sorry, I'm pretending there's a variable name. There's not. You know, in reality, if I was just doing this from a command line, I would actually do it that way. If I was just running a quick script on my command line. Yeah, it works. It's fine. It's actually totally fine. But using the bound parameter is like a best practice. When we use SQLAlchemy normally, and everything else we'll see in the tutorial, we'll generally be using those bound parameters, but it'll be automatic. You won't have to worry about it. We use the bound parameters so that we allow the database library to deal with literal values in a safe way and a way that's properly typed. And the biggest reason you'll hear is to prevent what's called a SQL injection attack, which is where if someone on your website puts a malicious string that has its own SQL inside of it, and you just embed it in your string, they could, in theory, well, many times in practice, mess up your database maliciously. So that's one reason. There's other reasons too. There's reasons for efficiency. If you were running that insert statement 100 times, the database would see the exact same string with different values, and you can make a prepared statement out of it. There's a lot of reasons that using the literal value is important. But it does work without doing it. So it's totally fine either way, but when you're doing more serious programming, you want to always use bound parameters for more substantial bits of code. But yes, it's not required. And I will often do literal statements like that just for something quick and dirty. Okay, so, and that is the end of that slideshow. So that's the engine. You kind of have more of an idea of an engine than you did 10 minutes ago, right? Good. So we get to the next section, and I can see how much time I have. So I went over that. Yeah, see, I went over time. Okay, so we're now going to go a little faster. Engine facts. Engine executing via the engine directly, when we said engine.execute, is called connectionless execution, which the engine makes a connection, does something, and then disconnects for us. And then when we use the connection object, we call that explicit execution. We control the span of a connection in use. And then the engine, usually uses a connection pool, which means that disconnecting often means that the connection, the actual TCP connection to the database or the file in the case of SQLite, is just returned to the pool. It's still in memory in your Python application. And in SQL, the string we send to engine execute is not modified. It's consumed by the database API as is. So if the database API has quirks like different bound parameter formats or escaping, engine execute will not help you with those. Everything else in SQLAlchemy will help you with that, but at this level, it won't help you. So it's more of a direct line to the database, as you'll get. All right, so that's level 1 of the onion. So level 2 of the onion is metadata, table metadata, and reflection and DDL. And now we'll see much more interesting things happening already. So what is metadata? Popularized by Martin Fowler, who wrote this book called Patterns of Enterprise Architecture. And it's a book that I read before I did SQLAlchemy because I knew a little bit what I wanted to do, but I read that book to get much more of an idea of what I wanted to do. It's a good book. Metadata is about describing the structure of a database schema, tables and columns, and the constraints and the types in terms of objects in your programming language. So in this case, it's data structures in Python. And once you have this data structure in Python that describes what a schema looks like, whether or not that schema actually exists, you can use that structure as the basis for generating a database schema and also for doing object relational mapping, generate to a schema. And you can also create a metadata structure from an existing database. We call it, in SQLAlchemy, we call that reflection. It could be called the introspection. So it's kind of like when you want to talk about the schema of a database, but you want that representation to be in Python, it's universally handy to have this basically data in your program that actually describes the shape of the tables that store data, which is why it's meta, because meta is always about describing the thing that is, or something like that. It's meta. It's out there. It's like, wow, meta. Data about data. Anyway. Oh, we're back to the slides. So then we go to the next slide. 2. So metadata. So when we get to the first slide, metadata, we see what SQLAlchemy metadata looks like. And we see the imports at the top. And what time do I need to go to? 2, that's not going to happen. Okay, we're going to go to 2:30 for this. All right. So schema, we deal with, yeah. Did someone raise their hand? Someone's just making fun of me. Okay. What's that? Funny ears. Okay, so metadata, table, column, integer, string. So these are objects that describe those things in the database. And then we have this structure called table. And so we create a new table object. We give it a name. The table object is going to be present in this collection of metadata, which is about table metadata. So the metadata object is a collection of tables. So it represents any number of tables, usually like for a single schema, but it could be for multiple schemas or part of a schema. It has 3 columns, ID, name, and full name. And then you can see the ID column is an integer column, the name is a string, and the full name is a string. Now the way table metadata in SQLAlchemy work, the reason it looks this way is that it's supposed to resemble a create table statement in SQL, right? Because we've all said create table, or many of us say create table foo, ID, integer, primary key, name, varchar 200. This is designed to look like that. So the people that know that love this object. The people that don't know that are like, why is this so hard to type? So yeah, it's designed to look like the same way that you do DDL in a database. That's why it looks that way. So this user table object describes a table in a hypothetical database. And it has all kinds of attributes, like the name we just gave it. .name is user. It has an attribute called .c, or .columns, which is kind of like an associative array of all the columns of the table. Now I say associative array because it's like a Python dictionary, but it's not exactly. So I just say associative array because it's not exactly the same. So you can access the different columns off, like name and ID. Those are the columns. It's a bit like a Python dictionary, but not really. So it can list out the columns that it refers to. Each column, so if we say, name call equals user table C name call is this column object, that has a type and a name and a parent table. So it's kind of like an XML DOM. We use the DOM in XML. It's a little like a traversable structure where you can go up and down describing this table. The table object has this thing called a primary key constraint. This is an object that tells us what columns comprise the primary key. It has other collections of foreign key constraints, stuff like that. And then the table object is at the core of the SQL expression language, which we'll do later, where we could say like user table.select gives us this construct that produces a select statement. So we'll see how once we have table metadata, we can produce any SQL string using the table metadata elements as the components of the SQL statement. So when we have table and metadata, we can create a new schema. So here, whereas the first example, there were these tables that kind of magically appeared when you first ran the script, this time we'll actually show how to create tables in a schema. We make a SQLite engine, and we didn't give it a file name. And SQLite has this handy feature called an in-memory database, which means it won't exist in the file system at all. It'll just be this little local database, bless you, in memory. And then when we say we have the engine, then we say to the metadata object, create all, which means create all the tables that don't exist yet. So we hand metadata to create all. It will then run. First, it'll ask the database, hey, do you have a table called user? And SQLite will say, nope, don't know that table. And then it'll say, OK, create table user with integer primary key and varchar name and full name columns. And notice we had said that user has an integer primary key and has a string for name. String usually becomes a varchar when you create a table in the database. And then it ran a commit, which is because some databases need you to commit that transaction when you create a table. SQLite's not one of them, but it does it anyway because it's harmless. So that's our user table, which now exists in the SQLite database, matching the table object we have in our Python program. So we have this nice synchronization between the two sides. If we make a fancy table, the point of this table is to show how you can have different data types. So if we want the varchar to be 50 characters wide, you say string 50. We have date time. We have like a numeric where you can give it the scale and precision. If you're working in finance, you'll want to use that type. We have an enumerated type, which will create a constraint. And you'll see all these fancy types here. This is just for illustration. Fancy table with varchar 50. And it has a nice, the type is an enumerated type, so it has a check constraint. So if you put any string other than A, B, or C into the type column, it'll throw an error from the database. That's a data constraint. So this is just showing the type system. You can pass either the class of the type, or if you want to send it arguments, you can instantiate it. And you have this syntax that looks a lot like SQL DDL. It's kind of what it's still trying to look a lot like DDL. So far, so good? Okay. So table metadata also allows for constraints and indexes. So in the way the next 3 sections of this talk will go, we'll start with one table, then we'll always add a second table, which refers to the first table. That's kind of how it always builds itself. So we had a table called user. Now we'll make a table called address, which has a foreign key column referring to the user column. So we do that. We use the same table structure, except when we make the user ID column, we give it another directive called foreign key. And the argument to foreign key is usually a string with the name of the table and then the dot and then the name of the column that the foreign key refers to. It can also be the actual user.c.id object. If you wanted to do that, you could pass that directly. But it's usually easier to send the string because you can actually make either table first and one refers to the other with the string, but you can make the address table before the user table. It's just when you actually say to create the tables, they both are present in the metadata. So we can actually say to the address table directly, hey, why don't you create yourself? And so you'll get the address table. And it'll have similar kinds of stuff. It'll have foreign key. User ID refers to the ID column of user. Foreign keys, we're OK, right? All right, good. Now that's the foreign key directive is very common, and it's basically a shortcut to creating a single column foreign key. If your table had a multiple column primary key, which we call a composite primary key for everyone that read the handout, you need a composite foreign key. So that looks like this. So if you had a composite primary key, meaning a primary key that has more than one column in it, and you wanted another table to refer to it, you would use a composite foreign key. So instead of saying foreign key on the column, you have to make a full-blown foreign key constraint object, which has two arguments. It has other arguments too. You can give it a name if you want. The first argument is the list of column names in the local table, and the second argument is the list of columns in the remote table. And for those of you who have done constraints with regular DDL, this is again how database DDL usually looks. It says if you have a constraint that's for multiple columns, you'll have at the bottom of the columns, it'll have, foreign key, blah, references, foobar, bat, So this again is designed to mimic the way the DDL looks. So if we create these tables, you'll get that there's the second. So here's the first table up there with the composite primary key, and then you go down, and then you have the single column primary key and then a composite foreign key, so that every row in published with story ID and version ID, those two columns need to match exactly to a story ID, version ID up in the story table. Right? Pretty straightforward. All right, good. And you see, we're using the engine too. Remember the engine? We're using it. We just have to worry that all those that we showed you those details in the beginning that were important, but the engine is very useful to us in this. We don't have to really deal with it directly kind of way most of the time. So we have the next exercise, and that actually enables us to catch up almost. Good. So this is to write a table construct corresponding to this create table statement. So this is another table called network, which will also have a single column foreign key referring to the user table. And then we will emit create all, which will emit the create table statement for this table, and it will skip those that already exist. And actually, I'm going to do this exercise too because I remember there's actually several more slides here before we get to the next thing. So we actually are not ahead of time. So I will type it too. So if you're doing it, just look down and type and don't watch me type. See me doing my typos. Right, nullable equals false. Sorry, I didn't show you that. Anyone? Next word? Great. If you're watching me type. Okay. There you go. Date. Feel free to call out. Yeah. How do you go back? Scroll up. Yeah, it's not because it's executing the code, so it's going to get all screwed up if you try to. There's ways to make it re-execute previous slides, but it'll mess up its, yeah. Scroll up. Yeah, use it right. That's the last column, right? Yeah. What did I do wrong? Parentheses. There's my columns. So when you do a create all, you'll see what's handy here is it'll break, so what it'll do. Because I put the wrong thing here. Sorry, engine. So it'll actually run through all the other tables in the metadata, because I just said create all. So it's going to check if all the other tables were already there, and they already were, except for network, which gave it false, so then it created the network table. And that's the network table. So now we have all these tables in our database. I want to kind of move, because at 250 is the break, which means we have to do SQL expressions until 250. So let me just go more quickly. Just the concept of reflection means that we're going to create a table object but not give it any columns, or maybe some. And then we're going to tell it, hey, can you please go to the database and load the columns for this table as it exists in the database, and then give them back to us. It's called reflection. So we say, we make a new metadata object, because the one we have already has the user table inside of it. So we make a new metadata object, and we say, hey, here's a new table to you, metadata 2, called user. Auto load is true, and please use this engine to auto load the data. So when we do that, you'll see the pragma statements again. This is how SQLite gives you information about a database. For other databases, you'll see, select from information schema, stuff like that. You get information about the user table. It gets the foreign key list and the list of indexes. So now we have this user reflected table, which has all the stuff that it loaded from the database. So that's called reflection. So if you have an existing database, like a WordPress database that you're moving, which I'd recommend, you could reflect the WordPress database without having to type out all the schema. It'll just pull it in for you. And I've actually done that with old PHP stuff. I've just used reflection to pull in the whole schema of like CMSs and shopping carts and stuff. So use reflect as columns. And then another way that you can look at what's inside of a database more specifically is this object called the inspector. And the inspect function is actually new in SQLAlchemy 8. The inspector is not, but this function is. Inspect is kind of this general use function that gives you the official information about something. And different objects in SQLAlchemy have a different inspect object. And in the case of the engine, it's actually this object called the inspector. SQLAlchemy.engine.reflection.inspector object. And this will give us, instead of giving us whole table objects, which it can do that too, it will give us more specific information like the names of all the tables in the database. And you can see we're doing some more deep SQLite calls. So there's the names of all the tables. If you give it a table, you can get you can get information about all the columns. And these are not column objects, these are dictionaries. So this is like raw information about all the columns in the address table. Which one's the primary key? And this is really handy because this is agnostic of data. You can run this on MySQL or whatever, yeah.
So it does all that, like the $$ or whatever.
Whatever has to happen, it'll do it. Yeah, I mean, it's an always in progress system because everyone's constantly coming with new curveballs. It could do better at, we don't yet reflect check constraints and triggers yet. We don't do all those, but there's room for all that to be added in as people add more stuff. But yeah, it does SQL Server and all the, yeah, there's a lot of stuff. It'll give you the basic details of a table for any database. You can get the foreign keys, so you get the preferred table and all that stuff for the address table. So it's pretty cool, and that's what the table, the auto load feature actually uses this stuff behind the scenes to produce the table object. So these are, let me see with the time, because I have to look 2:20. So we're 10 minutes behind. So I'll show you this one, because it's, the SQL expressions are more interesting, so we'll get to that in a second. So network, we're going to reflect the network table. Network reflected equals table, network, give it the metadata 2, auto load equals true, auto load width equals the engine, and we should get it. And then network reflected has all the stuff. And then the other one was using the inspector, print a list of all the table names that include a column called story ID. So this was a more tricky, this actually requires writing code for real. So I'll show you that because we're behind a little bit. For tname in inspector get table names. I'm probably gonna get this wrong too. For column in inspector get columns tname if column name equals story ID. Hooray. So what we did there was I iterated through all the table names. For each table name I called, give me all the columns, this column dictionary. And then for each column dictionary I looked in the name of the dictionary to see if it's called story ID. And if it is, then that table is a good one. We want to print out the table name. So in between the SQL, you can see the name published and stored, the two tables. And that exercise because we're falling behind. I just want to blow through a few of them. There's plenty more exercises to do. All right. The slideshow is over. OK, great. So then we'll go back to this. And then we'll see. I think that's the end of metadata. Some basic types. So some extra information about metadata. Here are types. The integer type. For int, string does varchar. Unicode is kind of a variant of string. It will do what the database wants to do to store non-ASCII data, like if you have UTF-8 encoded data, whatever syntax the database wants for Unicode. Boolean will generate the Boolean type, but if you're on MySQL, it'll generate like a tiny int. Things like, so it's kind of agnostic of whether the Boolean type exists on your database. Datetime, datetime or timestamp. And deals with Python datetime objects as input and output. Floating point values with the big .0000099, that whole thing happens at floating point. Numeric is precision, and you'll get back actual Python decimal objects using numeric. Those are some basic types. There's many more. The create and drop that I showed you, the variants are create all, table.create. So metadata create all, table.create, metadata.drop all to drop all the tables, and table.drop. So those are your four variants of creating and dropping. And what's also cool about metadata create all and drop all is that if you have a lot of tables that are dependent on each other by foreign keys, it will sort them in the correct order and drop the correct tables first. Yeah. A better way to do that is actually to drop all the constraints first. But not every database supports that. But there actually is also a recipe on the wiki to just drop all the constraints. If you have a database where you have circular constraints between tables, there's a way to do that too. But by default, it just figures out which table is dependent on which, and drops the dependent tables first. And then create all works the opposite way. It'll create the user table first and the address table. So that's handy, and that's metadata. So that's the metadata. So we general idea of metadata. We've learned something new about metadata, right? Table metadata. Okay. So now we're going to get into really, we're going to head up to, the break is in 20 minutes, right? Okay, and then we're going to plow through as much SQL expressions as we can in 20 minutes. And then after that, we'll have the ORM, and it'll be like a whole new world. All right, so SQL expressions builds upon the table metadata, like the onion, in order to compose SQL statements in Python. We'll build Python objects that represent individual SQL strings, statements, that we can send to the database. And the SQL objects are composed of other objects that each represent some unit of SQL, like a comparison of two objects, or a select statement, or a conjunction, such as and or. And then when we work with these objects in Python, they're converted to strings when we send them to the execute method of an engine or a connection. So it's a Python object all the time, unless you execute it. Then execute says, oh, I'll take this guy and make it into a string for you, and send that string out to the DB API. And that's how we usually are sending strings to the database API, is using SQL expression constructs, either directly or through the ORM. And you can also print them. You'll see that in a second. So we go to the third slide REPL thing. So the third slide REPL thing starts with the same exact table that we just had, because we're just going to stick, you'll get to know these three columns pretty well, so they'll be familiar. User table, ID, username, full name. Great. So there's your table. Create the table with SQLite, just like we did before. This is review. There's the table. And then as we saw before, we have a column called username. Maybe it was called name before. I may change the name. Username this time. Usertable.c.username is the column object. It's actually a Python object called the username column. And what we can do is this weird thing where if we take that column object and then we compare it using the Python double equals operator to the word ed, for some reason we're not getting true or false. Like this is Python. So if we say 4 equals 5, we get false. If we say ed equals ed, we get true. When you do a double equals in Python, you're going to get false or true, unless you do something in Python which is to override this magic method called EQ, which you don't have to know that really, but I'm just showing you what it's doing. Is that in Python you can overload most of the operators to do something else. So when the whole the SQLAlchemy is that the column objects and many other objects overload the Python operator callables, equals and not equals and greater than and less than, to produce a new kind of object that is specific to SQLAlchemy's system, which in itself is another column expression. So if I say x equals, and then it's basically this expression here, right? So x is now this weird binary expression object. I can just say x equals Jack, and that'll give me another binary expression object. So it's kind of building these like Legos, connected together using operators. So it's an expression system. It's basically like the operand operator in the middle. Every people might have built in their college programming courses little calculator applications like postfix or infix or whatever that stuff we did. So we have this new object that is part of a class of types called column element. If I do the MRO, you can see the hierarchy of SQLAlchemy binary expression column element. So column element is the base class of things that have like overloaded equals and Python operators and can be used as little atoms in a SQL statement. And this is more deep than most people even go. I'm just showing you what it looks like from my perspective. So when you take one of these little binary column expression things and you call string on it, you get a SQL string. And interestingly enough, the name ed has vanished. We get the string which says user with quotes because the database is a reserved word for user, dot username equals, and then we get this bound parameter username 1. So ed, actually, the string ed kind of vanished, but it's in there. So this is why I was saying before, it's very hard to not use bound parameters with SQLAlchemy because we didn't have to do anything. We just said, hey, the user column, compared to the string ed, and it became a bound parameter for us. So that's the string, and we'll see a little more of that in a second. You can combine these column elements with other ones using conjunctions. Like you can use the Python pipe operator, which is actually normally for a binary OR operation. It'll do an OR of two, a bitwise OR of two numbers. We overload that to produce an OR conjunction. And there's another way to do that, which is to use, and I actually prefer this way because I think it's more explicit. We use these two functions called and OR to produce conjunctions, right? Conjunctions are when you say x and y and z or b or q. Those are conjunctions, right? So in this case, we have 3 column comparisons embedded within 2 conjunction functions, and that rhymes. It's too cool. So yeah, so you can see the nesting we did here. We have this SQLAlchemy expression, which is user full name equals Ed Jones and username equals Ed or username equals Jack. And then you see when you print it, you get the same thing, except all the Ed Jones, Ed Jack, which as far as we're concerned, could be injected SQL vulnerabilities have been hidden away temporarily. So this is what the expression language looks like a lot of the time, is this kind of thing, producing these conjunctions and comparisons and other kinds of expressions. You can do comparison operators like greater than, less than. You can do is null. If you compare to the none constant, you'll get is null. If you were to say, as you might expect, not equals none, you'll get is not null. There's also an is none if you want that. You can do that too. That's a little more recent. Somebody wanted that. Okay, and then interesting here is the plus sign, the addition operator. If you take like the integer ID column of user table and say ID plus 5, that's a math expression, right? 2 plus 1 plus 1 equals 2. The ID plus 5, and you get a plus sign. But if I do the plus sign against the string, I get a different expression with a concatenation operator. And what this is attempting to reveal is that the behavior of an operator also has to depend upon the types that you're dealing with. So SQLAlchemy will deal with the fact that the type is different. And this is especially cool with some of the newer types we have, like we have support for Postgres array types and Postgres HStore types, and we have all kinds of fancy operators to compare arrays and concatenate arrays and do weird key value things with HStores. And we do it mostly with Python operators and some special operators, and it's pretty cool. So the operating system is pretty powerful. It's come a long way. This is what in looks like. If you want to say some column in this collection, so we want to say all the rows where the username is either Wendy or Mary or Ed, we could do an in, pass it a list of possible values. This is an example of if we have this same expression, the object expression, if we run it against different backends. This is an example of how to actually compile that string against the MySQL backend. We get the %s bound parameter format and user.username without the quotes. If we run it against the Postgres dialect, we get the user string is quoted. We get a different bound parameter format. So that's what the expression language is doing for us. Because even for something as simple as x equals y, the two different DB APIs want something different. That's how annoying the DB API is. But it's kind of the fact that the word user is quoted on Postgres and not on MySQL. We no longer have to worry about those things because the expression language will take care of those things for us. We don't have to use the expression language for that. We can still run a SQL query, but what's handy is that we can do it in Python. It's an object that we can more easily reason about. We can look at its structure, and it will automatically generate the correct SQL on the target backend. So that's why it's handy. So what happened to that word Ed? We said username equals Ed or username equals Wendy. Where did it go? Well, it's actually in there, and this is one way to see where it is, which is so the expression is this thing, and as we saw before, it's this string. It actually has, if we say to it, hey, compile it, it produces this object called a compiled object, which means it's the string form against a default database backend. That object has this method, this accessor called params. So if I say expression.compile, as I'm just saying up there anyway, it's the same thing. Params. So those are the bound parameters. So you can print. So when you print the expression, you see :username_1. The actual value for that is embedded in the object in the params structure. And if you want to see it more directly, when we say expression, it's a binary expression. This is totally deeper than most people go with SQLAlchemy. So this is good stuff here, because most people don't care about this, but I'm up here showing you. So when you have an infix expression, right? Operand, operator, right? It's got a left, a right, and a middle. Okay. So the binary expression means it's one of those infix expressions. It means it's got two sides to it. So expression has left side, which is the column. Expression has right side, which is this bind parameter object, which you can see has an anonymous symbol, and also the word ed is in there. That's the right side. And it has an operator, or I call it op. Yeah, it's eq. It's the built-in function eq, which is actually a Python built-in. Python has these, if I say import operator, operator is a built-in Python module which has little functions like EQ and not equal to and like that, LT. And these are actually the primitives of Python's expression. So if I say EQ 1, 2, it'll screw me up because I didn't do it right. Operator, get false, 1, oop. Okay, so we use those Python functions as representative of the fact that this binary expression is using the equals operator. So this is deeper than you need to know. I'm just, riffing. All right, so that's that. You know all about that now.
Is that actually used?
What?
Equals operator?
It actually, it's not, okay, so it's used in the basic way as a symbol that is like a constant referring to the equals operation. But if you have, it actually does get used if you keep calling upon a column that I'd have to look up in code, but it does get used in some ways. There are certain, like if you say, some of the other operators will call upon the function and then call back to the, I can't explain it that easily, I'd have to show you. And I'd have to go in the code and remember. But it does call through them in a little way. But it's generally like a constant because the operator EQ function is a fixed part of Python. So we have some other functions that are also local to SQLAlchemy, like the in op, the in, the contains operator. Anyway, so yeah, it does use it, but it's mostly as a symbol, as far as how you think about it on the outside. But people don't even think, you don't even have to worry about that. It's just if you just do that kind of thing, it's kind of done for you. It's okay. So when we have this thing and we actually do a select statement, and then we actually run the statement through the engine, you'll see it pulls out that it'll run the bound parameter, which you see as a question mark now because we're against SQLite, which has another bound parameter format called positional, and it'll pull out the word ed and use that as the parameter for the question mark there. So this is the expression language in action doing a select statement, and we'll see some more selects in a minute. Okay, so then we're up to exercise already. Okay, so we're at 2:47, which means I took way too long. So, right, because we want to have the break at 2:50, right? Okay, so let me blow through a few more, and this is just more of what we just did, because we're going to do the ORM after the break, basically. This is an insert construct, so we can do an insert from a user table. We can get the last inserted ID. We can run multiple rows in at once more efficiently using the execute many format, which we say an insert, and we give it a list of rows. This part I'm going too fast just because we're not going to have time to go into it, but you can review it later since you have the software. Run some rows in. This is what the select construct. Select username and full name from the user table where username equals ed, and it'll run that. You can select all the columns by passing the user table object to the select const function. You can do a where clause. So you see these select statements, they look kind of like SQL a little bit, right? Select table where. When we do the ORM, the ORM looks a lot like this, so we're going to do this all over again anyway with the ORM, but this is the core version of SQL. Select statements, you can put multiple where clauses will be joined together with and. Order by, select order by username. And then more exercises that we're not going to do, you can do them at home. Joins. We're going to see this all again in the ORM. So we're going to create the address table again here, put some rows in the database, and then we can actually join from the user table to the address table. Yeah, this is too much to go through this fast, but does it help to actually see a quick version of it at least? It's kind of fun to watch. Okay, because I know I'm going too fast. If you don't give it the on clause, it knows that there's a foreign key between the two tables, so it'll join them. Select from a join, select from. And then this is how to use subqueries. So we've gone too fast. One more minute, 2:49. One more minute. Subquery against address. This is a subquery. This is some group by. So this is where I was really ambitious, hoping that we would get this far. But I talked too long about the the equal sign. But you can see it's kind of a pattern here, right? You select in table, where clause, group by. You can then build bigger building blocks from a subquery. We'll do this again with the ORM too. It'll be the similar thing. So that's the select statement. Scalar selects. It's just so much detail. Scalar selects. The scalar select is when you select just one row and column, and you want to use like a correlated subquery. You can do all that. And then if you want to run an update with a where clause or an update with an expression, delete statement, and more exercise that you can do at home. All right, so 250. So why don't we do the break? I said to myself, I'm going to do as much as I can of the SQL thing, and then we have to do ORM because ORM is more interesting than all this. So, am I ready to go? Your minute is good? Okay. Everybody here? Great. So we're at the outermost layer of the onion. We've surpassed the edge of the solar system. And we have until 4:40 to get as much of this out as possible. And this time we do have more slides because I want to go over object relational mapping and what it means, the process of associating object-oriented classes with database tables. We refer to the set of classes, the objects in your Python world, as the domain model. So the most basic task of the ORM, and everyone knows this, is to translate between a domain object and a table row, and to answer your wife's text later. Okay, so domain object, application, object.save to the database, to your table row, class, this is just hypothetical, class.load your row into your object. Okay, that's that. Some ORMs can represent arbitrary rows, which means that the row is not in a table. It might be a row from a select of a lot of rows, and you want to get rows from the select statement and then make those into objects. You can do that too. A little less common of a use case. What most ORMs do is to represent three basic compositions, which are when we are composing together multiple tables to form some kind, or multiple rows to form some more elaborate structure. So here this diagram is attempting to illustrate parent object with a collection of child objects. We call that a one-to-many collection because there's one parent for many child objects. Each child object has one parent, many to one. The relational database represents that as a foreign key between usually two tables. So rows in table 2 have a foreign key referring to a row in table 1. So table 1 has the primary key, parent, and then the foreign key is in the related table. So from primary key to foreign key will be one to many, and from foreign key back to primary key is many to one. So the ORMs, all of them, most of them do this. Django ORM, they all do it. They mediate this relationship and make it look like a Python collection on the other side. So this is the big thing that ORMs do, is one to many and many to one collections. And there's another one called many to many, which I think is not even in this talk. It's in the website. We can look at it some other time. What else does ORM do? Other things ORMs do. Provide a means of querying the database in terms of the domain model structure, and we'll hopefully see a bunch of that. Some can represent class inheritance hierarchies using a variety of schemes. Some can handle sharding of data, storing a domain model across multiple schemas or databases. They provide various patterns for concurrency, including row versioning. And the reason row versioning is for concurrency is that if you load a row and it's version 12, and then some other things happen with that row elsewhere, and then you try to emit an update for row 12, it might go to the database and be like, hey, this row is actually version 14 now. Something else has happened concurrently so that your version of the row is stale. So that's one pattern for concurrency. There's other patterns. Provide patterns for data validation and coercion, checking that the data going in is what you want and coercing data into more of a format that you might need. SQLAlchemy can also do data coercion at the core level a lot too, and that's actually where most data coercion happens. we would say the ORM would be used for business level data validation and coercion. So not necessarily checking that a date is in the right format. That would be more of a data level coercion. Business level coercion would be checking that the date is between Tuesday and Thursday on this month because that's what the client wants. That would be more of a ORM level. So you can see at the ORM level, we're talking about domain models and business rules and things to do with the thing you're trying to model, not as much the nuts and bolts of what you're trying of the data itself, not as much data formats. Flavors of ORM. So this is the comparison I'm always making because I want to kind of show why SQLAlchemy's ORM looks the way it does. Two general styles of ORM are what's called active record and data mapper. So active record it generally has each instance of a domain object represent its own persistence. So here, using an active record style ORM, if we wanted to save a row in the user table, we'd make a new user object. User, name equals Ed, full name equals Ed Jones. And then we say user record.save. And when we say .save, that would emit, an insert statement directly at the moment you say save. And if you fetch the row again and you say save, it'll emit an update statement immediately. So that's kind of active record style persistence. The data mapper approach tries to keep the details of persistence separate from the object being persisted. So in this case, data mapper is going to be more like there's some kind of object referring to the talking to the database part of things. And then as we make a new user object, we kind of send it to the database handle thing. In this case, it's called a session, DB session. So we say user record equals new user, DB session here, take care of this user for us. And then when we're done with the DB session, we say commit to commit what we're doing. So that's, now usually the historical argument between data mapper and active record focuses a lot on configuration, where active record means that you make your class and your table all in one, and data mapper is where you have just your objects and then some other file maps them. And I think data mapper versus active record is more about not as much configuration of your models, but more about how you refer to the database interactivity. I think that's where it matters more. So ORMs may provide different configurational patterns, and most use an all-at-once, quote-unquote all-at-once, or declarative style where class and table information is stated together. So this is a hypothetical system where you might have a user class and an address class, and as you make these classes, they also have Python attributes that refer to, hey, this has a name and a full name field, which actually are columns in the database, and an email address field, and a user that's many to one, which means that there's going to be a foreign key. And this is pretty common. This is what Django ORM looks like. And SQLAlchemy is almost like this. It's a little more manual, but almost like this. A less common style keeps the declaration of domain model and table metadata separate. So you might say you make a user class that has nothing at all to do with databases whatsoever, just knows that about its fields. And then later, some other part of your app does this thing called mapper, which is going to take the user class and associate with this table. And another way that the data mapper pattern comes up in history is if you use an ORM in Java called Hibernate, you'd have your Java classes, and then you have a bunch of XML files that refer to how the mapping is set up. And that's data mapper. But even Hibernate has moved towards this model. Even Hibernate in Java, which is the most, where is it? This one. Has this thing, it uses this concept in Java called annotations, where you can actually still have this all-in-one mapping. So this is really where, even in Java, ORMs are going towards this kind of model. So the SQLAlchemy ORM is essentially a data mapper style ORM where we try to keep the details of persistence away from the objects. But at the same time, when you create a user object and you define it as a field called name and a field called full name, we know those are columns, but they're also part of the user object's behavior. So it's not like those fields are strictly about database. They are also about what fields the object has. So it's kind of necessarily mixed. But we keep the actual persistence details separate. Modern versions of SQLAlchemy use the declarative configuration, which is the domain and schema separate system is still present, but you don't really see it in normal practice. When I showed you that mapper thing before, that's actually what SQLAlchemy used to look like. And it still does that, but usually we use the system called declarative on top of it. This will make more sense when I show an example. The ORM builds upon SQLAlchemy Core, and many of the SQL expression concepts are present when working with the ORM as well. In particular, the whole thing with conjunctions and equal signs and greater than, that's all happening with the ORM as well. We still do all that stuff. So the expression language stuff will apply to that level pretty much. In contrast to the SQL expression language, which presents a schema-centric view of data, the ORM presents a domain model-centric view of data. And this is more of this fluffy, ephemeral, philosophical thing. When you work with the core, everything's in terms of the user table and the address table and the network table. And when you work with the ORM, it's a little different. It's still things are in terms of classes that are generally mapped to those tables. But we're thinking more in terms of how classes are related to each other, one-to-manys and relationships and inheritance. So it's a little more about how your domain model is structured versus how your tables and foreign keys are connected. Just a little bit. Key patterns that the object relational mapper uses. The big one, which we'll see, is called the unit of work. As you modify and create new objects, the unit of work keeps track of what you're doing and periodically will flush those changes out to the database. And then right as you're about to commit, it'll do a final flush of everything. And it does this in a very transparent and automatic way. So you don't really have to worry too much about when you save your objects. It'll just kind of be like, just give me your objects and I'll handle it. I'll push out the changes in the correct order in the right way as we need to do it. So it's very, very powerful, super duper feature. And I think the unit of work is really, why SQLAlchemy is a really great tool. Because it's when you put together like 20 objects and all of a sudden you see this whole big goes in of all the SQL works out, all the primary keys and foreign keys add up. It's great. The identity map is the concept of when you deal with objects in this unit of work system, any particular object will refer to a certain row in a certain table, which means it has a primary key identity. Every row that we work with in the ORM has to have a primary key. So every row is unique. The identity map means that you will only have one instance of a certain object with a certain identity within the scope of a particular unit of work. And that is something that is very handy. As you build more complicated systems, you really want to, if you load a certain object that's primary key number 5 from this table, if everyone coordinates on that same object in memory, it means that everyone's seeing the same view of data without it necessarily being flushed up to the database. So it's a very essential pattern. It's more essential than it might seem at first. Lazy loading means that you have an object that refers to a database row, but it might not have everything on that database row present in memory. It might have some references to some other tables. It might have some collections or many-to-one associations with it, and they might not be loaded. But then when you ask the object for this particular attribute, it will, at the moment you touch the attribute in Python, emit a query behind the scenes to load the additional information that you've asked it for. So if you had user has a .addresses collection, and you loaded the user from the database, it's not going to take all the time to go load the addresses collection as well, because that would be more work to do. When you say user.addresses, it'll be like, oh, you want the addresses also? Let me go back to the database and query the address table for those other rows that refer to me as their parent. And that's called a lazy load. It's kind of like a load as you touch an attribute. Okay. And eager loading is when lazy loading is letting you down. You can tell a query, hey, give me all these user objects and also query for all their address collections at the same time. And eager loading is something that we need to do with ORMs because we need to know ahead of time, in very many cases, what data we really need to get. And this is where you get that so-called object relational impedance mismatch, where you say that domain models and objects don't really match relational databases. This lazy loading, eager loading thing is where that mostly happens, because people will complain that the ORM emitted hundreds of queries when I didn't want to. And it really means to go around that, it's a totally solved problem, in my opinion, but you need to know sometimes up front which tables you really want to go get. And you have to tell it up front, hey, get me the users and the addresses and these other related things and do it in this way. and give them back to me. So it's kind of like an optimization, but it's pretty good. Yeah.
Is there a way to tell from a query object whether it needs to go out and do another load, if it needs to do a lazy load, or if it's got it right there available?
Okay, well, first of all, there would be some attribute that you'd be curious about, right? Yeah, there is, but it's not simple. I could add a method to do that. I mean, it could be done, yeah. It's not simple right now. You'd have to dig inside the query and look at the options. But yeah, I mean, you know, it's doable. It's not an API method, but yeah, you could. I mean, but the thing about eager loading is that generally, you're kind of writing a query that you know will be used in a certain way. So you kind of, yeah. Like I would say you shouldn't need to do that, but you know. Like basically if I don't need to do it, I'm probably doing things differently than how you're doing it, but that's, you know. Yeah, no. No, I don't know. I don't really know. Because what happens is someday I'll actually need to do that. And be like, that guy was right. Now I need it too. Because that totally happens all the time. So I wouldn't say you're doing it wrong. Because I add features all the time that like migrations. I didn't think anyone needed migrations until I needed them. So I wrote a migrations tool. Now migrations are great. And for years I told people they suck. So seriously. That's why I want, you know, just give me more use cases so I can learn more. Yeah. Method chaining, you'll see a lot of that. Method chaining is when you compose a query using several method calls in a row. You'll say like query dot select these tables dot where this dot where that. We saw that with the select a little before. It means you're chaining a bunch of methods. Each method returns the object to you so that, actually a copy of it. It depends on how it works, but ours does a copy. You get a copy back and then you call successive method calls, and the methods are chained to produce a final set of object state. You know, in classical object-oriented programming, you have the constructor, which has new constructor with this stuff, and then you say object.setName x and set this, that. Method chaining is the same idea, sort of, but you're kind of doing more of a line of method calls in a row where they return the object with more stuff each time. And we just use it because it kind of reads nicely. And then we go to the ORM walkthrough. Okay. So I have till 440, right? Yeah, I'm going too slow in general. So let's start the clock. All right. So when we do object relational mapping in modern SQLAlchemy, we start with an extension. And why this is an extension is partially historical and partially, it's just kind of how it is for now. I don't have a good answer. Called declarative base. And this means we're going to make that object base. You see we capitalized the word base. In Python, when we capitalize a word like that, it usually means it's a type or like a class. And base actually is a class. So it's a class, but it was created from this declarative base function. And we're going to build a bunch of classes on top of base that represent different tables. And all the information about these tables will be stored using the metadata object we talked about. The metadata object is actually present on the base class right here. Right there. So if we were to make a second base, it would have a different metadata. So the reason we make this base class from a function is because it's going to act as, again, a registry of information about a certain set of classes that descend from that base. So you can have as many bases as you want representing different hierarchies. An application will usually have one base. It's not too common to have more than one base. There's usually not a reason for that, but it depends on what you're doing. Okay, so we'll make our first class, which is, again, the same class we're making over and over again, the user class from the base. And then, so basically we make a subclass of base, call it user, and then we apply some information to it that looks like the information we have from the table metadata. So we have the table name, and then we have the column objects. You'll notice that we don't give the column objects a string name. We could. There's no problem, but we don't have to because declarative is going to do some stuff to apply the name to the column object after the fact. So we're doing some syntactical Python stuff so that we can make the user class with key equals value type declaration. Yeah. You need, right, so you need to give it either double under table name is one way. double under table, pointing to an actual table object is another way. By default, there is no system of automating that name. But there are easy ways to do it yourself. So we support all of those functions like automatic primary key column, automatic table name. You can do all that stuff, but it's not built in. There's easy recipes to do that because we would prefer that you define how that works. Because some people will have camel case class names and they want camel case table names. Other people will want table name underscore table name. Some people are using Oracle with 30 character identifiers and they can't do the big long names. So we don't get into all that. We just say, here are the tools, and we're not going to do it in this tutorial today, but there are many, with the collaborative system has lots of ways to automate all kinds of patterns. And it does a lot of stuff these days. So you can do all that, but you need to define it up front. And usually if you're building a really big application with 100 tables, it's no big deal to spend half a day coming up with your paradigms, with your patterns. That's what I say. The Reaper method here is optional. That's just so when we print it, you'll see a nice table. And there's also no constructor. You can do a constructor if you want. Declarative will give you a default constructor if you don't make one yourself, and which we'll see in action in a moment. So when we do the user class, we had this table name. The declarative system created this table object for us, and we know what that is. That's from our schema chapter, right? So there's the table with user and all the columns, just like we saw before. It put those column objects into a table for us with the metadata. It also put another object, which we're not going to worry about too much here, called the mapper. And the mapper is the object that is going to mediate the relationship between the user class and the user table. It stores all the information about how those two things are related together. And we start using our mapped class. So we haven't talked to a database. I mean, we created a table, but we haven't actually done anything with the database yet. We're making an object with the usual name of Ed and Ed Jones, and we assign it to the variable Ed user. So that's just a Python object. We can just print out the attributes that we assigned. And we notice that the Ed user object also has an attribute called .id on it, which was because we created a primary. I'll show you up here. We have a primary key column called ID. So because we did that, new instances of user will have an ID name and full name attribute present there even if we don't assign to it. It'll come out as none, which is different from regular Python object behavior. Normally with Python objects, if you don't assign something, you get an attribute error when you try to look at a certain attribute. In this case, the attributes that we've defined as part of the mapping will come out as defaulting to none. So this object has no primary key yet. We're going to rely upon the fact that the database can automatically generate new primary key identifiers for us when we put it in. So now we'll talk to the database. I thought we had. Okay, we'll create the tables. Again, same thing as before. We have tables, metadatas, create all, and you get the same table we've been seeing, more or less. Create all. So to persist and load objects from the database, user objects, we use this thing called the session object. So from SQLAlchemy ORM, import session. And the same way we pass the engine to metadata.createAll, the engine has a source of connections. It's not a connection itself, it's a source of connections. We hand it off to the session object so that the session can do what it needs to connect to the database and control the scope of that connection and then disconnect. So again, the engine really, in normal practice, we don't deal with it. We just pass it off to other objects that know what to do with it. So we add our Ed user object to the session, and you actually can see it at this point in a list called session.new. And that means that the user object is what we call pending. It doesn't actually refer to any row in the database yet because it hasn't been flushed. So it's in the .new collection, meaning it's pending. And when we actually want to talk to the database, we're going to do a query. The unit of work pattern is like, oh, you want to do a query, so let me first flush out everything that's pending, everything that's in memory that all the new information you've given me that isn't in the database yet. I'm going to flush it out to the database so that when I do this query, it will have the advantage of having all the rows available to it, so that if I query for users named Ed, I will get that user back. Right? This is the whole leap of paradigm here, that nothing has happened yet. The database has no data in it yet. We added it, but it's deferred. It's not going to flush the data until you absolutely have to. So what this is also called auto flush. Auto flush means that it's going to flush for us each time before we do a query. We can turn that off sometimes, because sometimes we don't want to auto flush. Sometimes we have a lot of data that isn't ready to go in the database yet, because it might have data, yeah.
At this point, would it be committed?
No, it wouldn't be committed. So what's happened here, we haven't even, someone had asked earlier about the engine being deferred with the connectivity. We haven't even connected to the database yet. Even though we have an engine, we don't even know if our database URL is valid yet. Well, we have to create all. We know that. But so if we hadn't, we wouldn't know. So the session doesn't know about the database. It knows about the engine. So as we say query, it's going to start this whole chain of events where, oh, you want to flush first. Oh, I need to actually create a transaction to do that first. I need to connect the database first. Let me connect, start a transaction, flush the data, do the query. Now we're opening the transaction. And that's all going to happen with this press return. So we'll do that. So we have the begin and insert the row that was pending, and then we go back and select it. Because we call the little getter call first, it's going to do a limit of one row, and we get back the same object. And that is the unit of work in a query in a nutshell. This is the ORM doing what it does. 3, 4, so we have 1 hour. Okay. So far so good, right? I'm going because I like to talk. When I do it in my head, it's like, oh, I just go through it. But when I actually talk, start talking. So now that that .id is no longer none, it's now the number 1, because the SQLite database gave us a new primary key identifier of number 1. And then because we talked about this identity map where any object that refers to primary key number 1 in the user table within the scope of this session will be the same object. So we have the ed user object that we added to the session, and then we have the R user that we just queried for. They're the same object, because it basically goes through the database results. It iterates through the rows. It gets the primary key from each row. It says, hey, primary key number 1, let's look in the identity map for that identity. Oh, we already have it. It's this ed user guy, so return that. It's the same object. And that really, it's hard to explain how cool that is, because it really is quite critical. Yeah?
Just to make sure I get this right, it's not comparing it, it's not a type comparison.
It's the same object.
An actual object.
Yeah, it's the same. See, it's the same identity. If I go ed user, dot ho equals the, or user ho is right there. It's the same object. Because it's the same session. If you had a different session, it would be a different object. So there's only, while we've persisted one object and loaded another, there's only one identity in the session, so it uses the same object. So that's the identity map. And that's what it means, is that we can change the state of this object, and everyone coordinating on that session will see the same state without us having to insert the row and select it again. So if you're doing, with one object, it's kind of contrived, but if you have if you're loading thousands of rows here and there and everywhere, and a lot of those rows are being modified here, and some of them are being loaded here, some of them are being changed here, that the ones that are in memory together are coordinated. First of all, it stays as memory, right? Because you'll have only 1 instead of 3 copies of it, and then they'll all have the same state. So if someone changes a value here, it wasn't flushed yet. That's the whole thing, because the flushing is deferred. So if something wasn't flushed yet, you want to make sure every part of your program looking at that same session sees the same state. And it works pretty well, yeah.
If when querying the database it found that the object in memory is sort of behind, will it sort of update that same object with new data?
Right, so the issue of objects being behind is a tricky one, because by default it will not do that. What the object can do is it can be in a state called expired. When the object is expired, we erase the attributes on the object. The object stays, but the attributes get erased, or sometimes just some of the attributes, but usually all of them. The primary key identity stays associated with it in a special attribute. And then when that object identity is hit again, it will refresh it with the new data. So it'll be expired, but it'll get the latest data when you load it. But normally it doesn't do that. But the thing about expiration, and we're actually going to go over this some more detail, expiration by default is when the transaction ends. So when you're in the scope of a transaction, the ORM kind of goes along behaving as though the transaction is entirely serializable. you know what I mean by that? Who knows? This was in the handout. Who read the handout? Transactions are usually isolated from each other, meaning that as you go in your transaction, if someone changes something on the outside, if you have a high level of isolation, you won't see that change inside your transaction. If you have an isolation level called repeatable reads turned on, it means if you load a row, and then you selected that row, and you're in a transaction, someone else out there updates the row. You then select that same row, but you're still in your transaction. You will not see the new value. You'll see the old value because it's called a repeatable read. So if you have repeatable reads turned on, you could not actually see that new data. So yeah, that's the idea. The idea is that this works really well with the repeatable read model. Now, it's true that when you use Postgres or MySQL, you're probably not in repeatable reads by default. So you can't. This is the part I really haven't figured out how to explain yet. Is that normally, if you're in a transaction, you don't generally care about a concurrent transaction, and if you did, you would have repeatable reads turned on. If that makes sense. It's not a great answer because some smart person could totally shoot me down with that, but it's kind of how it works out. Is that the ORM by default assumes a highly isolated transaction, and in reality, it might not be, and you can expire things manually and have it force itself to reload, but normally you don't want to. When the transaction ends, then the transaction is over, then it expires everything. And then the next transaction, if you were to keep using those objects, would totally all refresh themselves when you hit them next. And we're going to see all that. So we can add more objects using add all. And we can change something about the ed user. So if we look at session new, we have all those objects that are pending. And if we look at another collection called session dirty, we can see that the ed user has changed. Excuse me. And there it is again. I predicted my own slide. And pending, as I just said. And then, now again, none of this stuff has gone to the database yet, but when we commit it, this is like doing a query, auto flush, or in any case, before we commit, we have to flush everything and then commit the transaction. So we do commit, press return and run code, and then you'll see the update of our Ed Jones happens, and then the user rows, and then the transaction is committed. And now that expiration thing has actually happened. If I show you the contents of eduser.dict, you'll see it's actually empty, except for that ho-ho thing I put in there. And I'll show you that, assuming the slides go the way I think they're going to go, this should refresh itself as we look into it. So after the commit, there's no transaction. The session invalidates all data, so that reaccessing objects will automatically start a new transaction and reload from the database. So this is an example of lazy loading. Ed user, who I just showed you, is empty. I'll say ed user dot, hey, what's your full name? Oh, I don't know. I just expired. I should go back out to the database and find what my name is. So let me start a new transaction, get the whole thing going again, do a select, and now we're back in a new transaction, and now we know that the name is Ed Jones. And if you look in Ed user's dictionary now you have his full name and his ID and his name are all loaded again. The SQLAlchemy session, when in normal usage, there's other ways to make it do different things, but normally, when there's no transaction present, it assumes it knows nothing about the data. And it expires everything, and it assumes that I can't tell you anything about this database because there's no transaction. You never really look, if you think about it, you never really look at the actual physical table in the database. You look at a transaction's view of that table. Because with isolation going on, you don't know if the table you're seeing is actually what's physically in the database. You could be seeing just the certain not repeatable read version of it. You don't really know. So SQLAlchemy always considers the transaction to be the only real source of data, because that's all you can really see. Yeah?
Is there either a way to flush the data and not end the transaction, or do the commit but still not having expired?
Both. You can flush explicitly anytime you want, and you can turn off the auto expire on commit, which is actually pretty common. Especially for web applications, you want to commit the transaction, then render a template, we turn it off. But that's not. But that's when you see what you choose to do that. It used to be that way by default, but we had people saying, "Oh, it's loading the old data." So the defaults we have now work really well, and you can turn them all off. Because I was really mortified by that feature when I first was presented with the fact that it should do that, and I realized after a long time that it is correct, but it really rubbed me the wrong way for a long time. We do expire unconditionally after rollback, though. Rollback we can't. We tried to make it, but there's no way to do it. So it expires because it's a rollback. It was a catastrophic failure. It's not a big deal.
have a flush will make it visible in your transaction, but not theirs.
Right. Your again, it depends on the. If you were using MySQL with either MyISAM or if you had your database with read uncommitted transaction isolation level, means you have something called dirty reads. That's the only way they would see what your transaction is doing before you commit it. Because the way transactions work is if you have dirty reads turned on, that means that other transactions can see what your transaction is doing before it's committed. And dirty reads is usually not in practice. Usually, even MySQL with MyISAM, I think, with InnoDB rather, defaults to read committed, which means that you can't. No one can see your rows till you commit them. Most of the isolation levels deal with what your transaction can see of other committed rows, but dirty reads are the one that involves uncommitted data being visible, and in most cases it's not visible.
So turning off the auto expire is really the right way to deal with. I'm doing something I want other people to see the 3 or 4 users I've just added, but then I want to keep going.
You either have to commit that data. Well, the data has to be committed. There's really no way around it. Right. You would take off the auto expire. Yeah. You're right. Right. That's how you would do it. Or sometimes it depends on what you're doing. Sometimes I'll actually run 2 sessions at once. If there's certain data I want to go out and the rest of it doesn't, I'll have one session for the things that I want, like a log table. I'll do that a lot. I'll have a separate session for committing to a log table. Let's see what's next. Probably relationships. Okay, this is rollbacks. I'll do this quick. I think we get this. Make Ed's name Eduardo and add a fake user that we don't want to save, add him in, and then we do a query. We get auto flush. The username has changed. We insert a new row. So we want to roll that data back. We say rollback, and now the data is gone from the database. Everything expired. Ed's username, okay, no transaction. Oh, let me go back to the database and get my name. There it is. His name is back to Ed. And then the fake user object that was Eduardo, the fake user that was invalid, is now not in the session. It's been evicted, even though the object still exists. And when we query for the table for Ed and the fake user, we only get Ed back. So that's just basically how the expire model we just talked about for a while works with the rollback. It works really nicely. Not that different. There might be an exercise. Uh-oh. All right, so to get to 440, let's do 3. Let's do till 54, which is only 2 minutes. There's not enough time, but I want to get through a lot of slides here. Okay, about 30 seconds. Here's the table. Oh, here's time. Add them in. Session flush. That's flush. So that's a flush without a commit. So besides the typing, it wasn't, okay, people, okay, fine. Here's your network. I gotta get better at administering exercises. Okay. Any major questions on the network, the exercise? Good, great. Okay, ORM querying. So we go back to this whole thing with the SQL expressions. User.name equals ed. Produces an expression. So so this is basically the attribute on the user class. It's not quite the same as a column object, but it acts the same. It's an instrumented attribute, and you don't have to worry about that too much. But it acts like a column. The column is actually there, which you don't need to worry about. But if you cared, it's in here. There's the column. That's a topic for further study. It acts like a SQL expression object. If we want to use the select function that I whizzed through in the core before, which you hardly got to learn at all, you can make a select and pass the user tokens to it, and you can get a. And if you wanted to actually run a plain engine level execution, you can do that with the session using this special method called give me the connection that you're using, execute a plain core SQL line, and you get the select user and Ed Jones. Now you can do that, or you can use the query, which is the ORM version of how to emit select statements. So you see here we got the result proxy back. This is all stuff from core basically with a little bit of ORM in it. But if we want to use the ORM normally, we just do that. So we say session, the database session, dot query, parentheses, tell the query what you want to load. In this case, we want to load user objects. Filter them on a SQL expression where user.name equals ed, and then order by the ID column of the user table, and then we're going to say query.all. Give me all the objects from this query. You get the SQL in your log output and a list with the Ed Jones object. Pretty simple. You can also query for individual columns, because we said session query user as a class gives you user objects. If you query for user.name, user.fullname, you get a tuple back. Tuple or tuple? Tuple. You get tuples back. They're not objects, they're just the strings inside of a tuple. They're actually named tuples, but I'll show you that some other time. You can mix them together. You can say user, give me the user class, and separately the username column separately. You'll get tuples with user objects and strings in them. So if you want to join a bunch of tables, you can get all mixtures of objects and column attributes back at the same time. Yeah. Right. So Right. So the session query is this object that again doesn't do anything until you evaluate it in iterative context or call .all or some other methods I'm going to show you in a second. So you iterate it to make it actually do something. It doesn't hit the database until you iterate. So besides iterating, you can also do array indexes. You can say session query user, order by user ID, and give me the second element of the third element of the so-called list, which means it's going to actually emit a query with a limit and offset. So index 2 means it's just one element of the list, and index of 2 means an offset of 2. So SQLite, Postgres, and MySQL have these keywords called limit and offset, which allow you to skip some rows in the query and then return just a certain subset of rows. Other databases like Oracle have more Byzantine ways of accomplishing the same thing, but SQLAlchemy will do automatically for you. So if we want just the second element, and usually when you're doing index access, you want an order by, because relational results are not inherently ordered. Array slices, position 1 to 3 will give you just a different limit offset, no big deal. This is, Django does this too, everyone does this stuff. The where clause is either by the filter by method, which takes a keyword name, like filter by full name equals Ed Jones. It's convenient, it's quick, you just put the name, and if you want to do more of an expression, you can use filter. So there's filter by and filter. They're same idea, but filter accepts expression objects with the double equals or greater than, less than, or, and then filter by just takes keywords. It's more of a shortcut. And they're separate because people were confused when we had them together. You can actually do keyword arguments, but people didn't like that. They were confused by it, so we don't do it like that. We have two separate methods. Okay, and you get that. And if you want to do conjunctions, particularly or, you can pass the or into the filter. So filter where full name is ed or user ID is less than 5 is kind of a silly query. Get that, you just get the results. If you call filter repeated times, like filter where username equals ed, filter where user full name is ed Jones, you get an and, right? This is all good? Pretty simple? Good. Some variety for returning results. So here's the query. So right now, as we said, this query has not actually done anything. It's an object. It's not a result yet. We can do things to it to make it give us results, such as .all will give us a list of all the objects. And we can say .first to give us the first row. And you can see when we do first, it actually modifies the query to add the limit offset again so that it only loads the first row. Now, different from first is one, which means that we want to also assert that this is exactly one row. And when you run one, it doesn't do the limit offset because it's assuming, it's not assuming, it's going to check, but if it works correctly, we shouldn't need to limit offset because there's only one row in the query that you've asked for. So it doesn't limit offset. Now, if you do get more than one row back, or if there's no row, first of all, you get an error. So say we get no rows returned, you get no rows found for one. And if there's more than one row, that's why I didn't do a limit. As soon as it gets to the second row, it does this other error message, which is multiple rows were found for one. So one is kind of like first, except it's going to actually run better because it won't do the limit offset. That won't mess things up. And then also will throw an exception if a row was not found or too many rows are found. So it asserts just one result. You would use a try except. Yeah, you would do that. I do it a lot. It's really good when you write your typical web application where you have like, RESTful /get/1. You say try load ID number 1 except no object found, abort 404, right? Because there's no row found, it's a 404. That's kind of how we do it. So I use it a lot for that. Okay, so there's some quick ORM querying exercises, and okay, we're doing okay. Because I really want to get to every slide, because you'll learn a lot. So we're going to go to 404. Go. Produce a query object representing the list of full name values. So query for just the full name column from all user objects in alphabetical order by alphabetical order by the full name. Then call all in the query to make sure it works. And then if you get that far, you build a second query from the first one that also selects user rows, I don't even understand this, with the name Mary or Ed. Oh, I see. The first one's not with a where client. All right. So yeah, first get all the full names. It's all of them. And then do a filter that will give you Mary or Ed. And then return only the second row. So it's the same kind of idea where we're just regurgitating what I just did, but it's all in the... What was that? My microphone? What did I say, 404? Oh.
Right?
So now you hear me, right? Oh, cool. Who knew that red means empty? Well, how is the light going on? If the battery's dead, why would there be a light? Yeah, exactly. Yeah. All right, so everything we've done always has a user. Then the second part is always the lightning round with the address table. So it's really boring. I'm sorry, but I've been using this example for years. So the address table, again, same idea as before, where new table, address, primary key identity. We just stick with the surrogate primary key because we're lazy. Email address is what the data this table stores. It has a many-to-one relationship to the user table, which with SQLAlchemy, we have to tell it twice. Sorry. Yes, we give it the user ID column, which has the foreign key to the user table. So at the core level, we tell it about the foreign key. And then we have the option to tell it that we want the ORM to maintain that relationship as well. And how do we do it? I should really just add a feature to do the foreign key for you, but right now that's how it is. So there's the foreign key, and what happens with relationship is you'll notice relationship didn't really care about us saying, hey, is this many to one or one to many, and how do you want me to join? The relationship looks at the foreign keys you have and figures out what you want. That's actually why we do the foreign keys separately, because it looks at the way the tables look and then formulates how it wants to do things. Now, say we had the user address table. Say they were tables in WordPress, and we wanted to reflect them. We would reflect just the foreign keys, but we wouldn't know about the relationships. We would have to tell it, hey, if you have a foreign key here, we want posts to comments to be one to many or whatever. So we would use relationship, and relationship would be like, hey, okay, post to comment. What is that? Oh, okay, I see that comment has a foreign key to me, so this is a one to many. It knows that. And relationship is a really, really major construct that has a lot of options. You can make it join in different ways. But 90% of the time, it's just straight up, you give it the name of the thing to join that it's relating to, and it will, based on the way the tables are constructed, figure out how it should be referring to it. So we say that address.user will be its parent user, and then we give it this little other directive called backref, so that when we have a user class, it will magically get this .addresses collection that refers to the one-to-many. And that's the great truth of the relational database, is that every many-to-one is a one-to-many on the other side.
Find this in the user class?
Yes, you can. And you can also define two relationships and point them to each other if you wanted to. People usually use backref because it's a shortcut. But you can have two relationships, and you can have two relationships where one knows about the other, but the other one, you can have them not know about each other too. And you probably don't. There's some nice in-memory things that happen with the backref, but technically they don't have to know about each other. But you probably want them to, because there's a lot of stuff that makes it work better. But yeah, options. There are options. All right, so that's address, and then the usual fanfare to create all. User's already there, network from our exercise, and then there's the address table, foreign key. We've seen this. That's why we built from the inside out. So this is like old hat now. Okay, so we make a new user called Jack. Full name is Jack Bean. And in the spirit of all the mapped attributes being present by default, instead of Jack addresses being none, it is an empty list, because one to many means that nothing means an empty list. A many to one, nothing means none. But in one to many, nothing by default, always by default, there's always options, means empty list. So Jack addresses has this list that's there without us doing anything at all, except for the relationship. All right. So we can populate it. You can say list.extend or list.append, or you can assign a new list, which will replace the old list. You do whatever you want. It won't really screw up. So we make 3 address objects. We assign them to address. So these address objects will now, because of that backref thing we did, they will have a .user pointing to Jack, and Jack addresses points to them. It's called a bidirectional relationship, and I'm pretty sure I showed it here. Good. So the second address object, Jack.addresses1, is the address object, and if we look at that address object at the .user, it goes back to the Jack object. And this didn't. So what happened here that's special is that we didn't actually put this in the database yet. It's just doing it in memory. It's basically using an event, so it intercepts the fact that we're appending an address, And as those events come in, it goes, oh, let me set the parent to the other side. So that's the event model at work. So that things kind of make sense, again, before we flushed. We're trying to reduce our dependency on having to select from the database before we really should have to, because we know it's in memory. So this is concept here. Everyone kind of grokking what's happening here? All right. This is more conceptual stuff. Okay. So we put Jack in the address. The next thing that happens that's magic is called a cascade. We added one object to the session, and there are rules called cascade rules that have defaults called please cascade all the add operations for us by default, which means that all the objects attached associated with Jack also go into the session at once. So we don't have to, it's not like, so if we had like an active record ORM, we might have to say jack.save, address1.save, address2.save, address3.save. With this, the way this works is that it's more intelligent about it. It cascades all the objects in, and also it will flush them in the correct order, because you know the Jack row has to go in the database first, because it has the primary key that the address rows will need for their foreign key. And because of constraints, the C in ACID, we need the user to be there first. Otherwise, we have to use an update, which we don't want to do because the user ID might be not null, and you know what I mean. Okay. Commit, and you get all that stuff in the database. You get the user and the addresses. So it was really very little relational database stuff. It was pretty much making a user object and putting address objects onto it, and just a little bit of, oh, add it and commit. And all that came out for, not a lot of typing. Okay. After expiration, so we committed the transaction. So as we know, the default behavior, which we can change after committing, is that everything is expired, which means that the Jack addresses collection is gone because we don't know it's in the database now. There's no transaction. We want to see Jack.addresses. Oh, let me start a new transaction, make a new connection, and go load both the Jack object, because we lost his state as well, and the list of addresses. So you get that back. You get a new transaction, you get the user row, and then you have the lazy load of the address collection. So it selects all the columns from address, and the where clause, you can see it takes the primary key of Jack and sticks it into the question mark there, related to the foreign key of the address table. And what's cool about this is that we don't need to query the user table a second time. The address collection can be loaded by itself, even though it joins to the user table. The part of the query that is the user table gets replaced by this little bound question mark, and we stick the number 5. You see what I'm doing here? Good. That's a lazy load of a relationship. Collection lazy loading. ORM 101. All right. And then if we hit, now here's where we're not the same as other ORMs. That collection is now in memory. So if you hit the same collection again, it won't go back out to the database a second time. Unlike another ORM that starts with D. It won't go out a second time. It's got it in memory because it has it in memory. It basically has a list, that's Python list, that's instrumented. It knows when we add things to it. It knows when we remove things. And it's got that list. So if we hit Jack addresses again, it just stays there in memory. Okay. What are we talking about here? Collections and blah, blah, blah. Okay, right. So if you want to, so one thing that happened here that was important was that the ORM took the job of taking the primary key of the user table, and it totally handled the fact that that primary key number is present in the foreign key of the address table. It handled putting the number there in the first place, and it handled checking for it when we do the query. So we don't have to use it, we don't have to worry about primary key and foreign key numbers or attributes when we persist, and we don't have to worry about them usually when we query. So how do we change things to do with foreign keys? Because people will ask, like, I want to change foreign key to something else. What do I do? You can manipulate those values directly. You can do that. But the ORM will just let you do it, but won't really help you with it. If you want to do it the ORM way, you don't deal with the PK and the FK stuff. You just deal with the actual relationships in memory. You here take the first address on the Jack object and say .user is now Fred. So Jack, the Fred object is now the parent of the second address on Jack. So if we run this, it'll commit, it'll do the update. So it'll update the user ID of the address row that we're talking about to point to the Fred object. and then we commit. So now the Jack addresses collection, which used to be 3 addresses, is now only 2 addresses, and the Fred addresses collection is now the new. So it moves. So basically, we did a manipulation of a foreign key attribute, but in our Python code, we didn't have to worry about it. We just moved the object, and the ORM, for something like this, knows just to update the foreign key in the table. Right? Got it? Good. Good. Doesn't always work. Sometimes there's problems. So the query can select from multiple tables at once. This is an implicit join. Implicit join means we're going to get from 2 tables. We're not using the join keyword. We're just going to get 2 tables in a Cartesian product, but then we're going to filter where the ID of the user equals the user ID of the address. So you'll get basically this product here. So it just has the from clause of the select has from user comma address where user ID equals address user ID. So that's called an implicit join, meaning it's joining the 2 tables but not using the SQL join keyword. It's basically the equivalent to an inner join. If we want to actually use the join keyword, you actually call the .join method from the query. So same exact query, except .join from user to address, and you get the same results. User select from user join address on clause user ID. So the way join works is the first argument is the right side to join from. The second argument is the on clause. And the left side of the join is determined by looking at what the query is selecting from the leftmost entity by default. So session query, the user is the leftmost entity, .join to the right entity address. If you want to reverse it, hopefully this is the second slide. Not yet. Well, OK, so I'll show that in a second. Another way to do join is to just pass it the name of the relationship. So instead of saying query user.join address, comma, user.id equals address.user.id, you can say, hey, give me the user address and join them on the user.addresses relationship, which represents that connection. So just doing user.addresses will give us the same join with less typing and without us needing to remember which column or even know which column in user addresses points to each other. So this is where the ORM is abstracting away us having to worry about how those 2 tables are joined together. We configured it. It's not like the ORM decided how they're joined together. We know how they're joined together because we configured user and address ourselves. But once that information is given to the ORM, we can use the ORM's knowledge of that so that we don't have to worry about it all over the rest of the code. So that's a little more join, and then more join. Join will also figure out very simple joins just using the entities. So in this case, the user and address tables have just one foreign key between them. So if you give it nothing, if you just say, hey, I've got user and join to address and figure it out, if it's unambiguous how to do that, the fact that there's only one foreign key between those 2 tables, it will figure that out automatically as well. And if it can't figure it out, it'll throw an exception. So it's fairly safe to do like that. A lot of people do it like this. I don't join like this because if someday I go and add another column to my address table that also points to user in a different way, this query will not work because it'll be like, hey, I don't know how to join those tables anymore because it's ambiguous. So I tend to use the more explicit approach of giving it user.addresses. That's what I do. But I see a lot of people doing this, and it's certainly supported. Cool? Okay. All right, so once we do the join, now the user entity and the address entity both refer to columns that are available in our query. So if we query for the user.name, and then we join to the user.addresses collection, we can filter on columns that are either in the user table or in the address table, and they'll all be put into the where clause equally. So here we load usernames for users that have an email address of jack@gmail.com. And then we get Jack as the username that has that particular thing. So the class entity is basically how we refer to that column. So basically the column name, the name column and the email address column have a lexical identity in the SQL statement that is referred to by their Python identity. So their Python identity relates to their lexical identity. So anywhere you use user.name, it'll be that same column in the table, in the query. And that, maybe when I show you aliases, that'll make more sense what I mean by that. Like, we're not using strings to figure out what the name column, we're not saying select quote unquote name, dot quote unquote user email address. We're putting these objects in that represent real elements within the SQL that we spit out. And that has a lot of importance, actually. If we want to do the join in reverse, so remember I said before, I should have had this slide earlier, when I said that the join will join from the leftmost entity to the right, suppose you wanted to join from some other entity, you can say, okay, we're going to get user and address objects, but select from first the address table, join to the address.user relationship. So it's the same thing, it's just going to reverse it and give you select from address join user. And that happens sometimes if your query is being written a certain way and you want to do select from. It's totally useful, and I need it quite often. Getting the same result again, users with their addresses in kind of a product. Okay, so that's joins, and we're going to obviously have a little quiz on that. And then we're going to do aliasing. So are people hanging on? Good. So aliasing gets to this fact that I was talking about when we talk about the user.name column and the address.email address column. It's kind of this lexical identity that always represents the same thing in the query. If we want to have two different versions of a column in a statement, so like we want to select from the email address from the address table in one way with one criteria and then select the same column in some other way, and what we're doing here is we're going to join them together to do something interesting, you need to, in SQL, create an alias for each of the tables you're selecting from. So the same exact logic applies to SQLAlchemy querying, and also the core system does this too. You want to make an alias of, because we want to select from the address table twice within one statement, we make an alias of it. Two aliases to be specific. So there's a function in the ORM called alias, and we call the aliased function on the address class, we call it twice to make two different objects. So A1 and A2 are these little alias objects that look a lot like our address class but represent a different lexical identity within the statement. So we select from the user table, join to the A1 alias, and then also join to the A2 alias, which means it'll know based on the foreign keys that we want to join from user to each one. And then filter where A1 email address has one address and A2 has a different one. So the effect of this query is we're going to get users who have both of those email addresses, which is obviously the username Jack. So we call that, we get Jack. And then we see in the query, we see that the join to address as address 1 on blah, join to address again as address 2 on the. So you see, the aliasing also created this anonymous name for us that we don't have to worry about. So aliasing creates anonymous names for us, figures out what they are. So anytime we refer to A1 in our query, it'll talk about address underscore 1. Anytime we talk about A2, it'll refer to address underscore 2. Now also, if the query were different, that number 1 and 2 might be number 5 and 6. It doesn't matter. It's called an anonymous alias, and it comes up on the fly, and it just remains consistent with itself. So we're being basically shielded from a lot of kind of pedantic details of the query using Python objects. So the Python identity is what represents as how you represent the lexical identity of something in a statement. Does that make sense? Yes. No, technically, I did it to make it clearer. One of them could be the address by itself, yeah. Just only one of them has to be alias. But I made them both alias because they're both in the same role. It's a little cleaner. But you're right. Only one can be alias, not the other one. Okay, so subqueries. So aliasing doesn't just apply to a class. And this is stuff that if I hadn't sped through the core tutorial so much, you would have seen also. We did the same query there. You can also have an actual query, because anything that's a source in SQL, anything that's a source of rows can be packaged into a little name in a query and selected from and joined to as something to join from. So here we have a subquery. We call it it's a plain session query. and we say, hey, query, give us the count of the address ID column using a new construct that I didn't show you before too quickly called func. In SQLAlchemy, func is how we get to all those SQL functions, all the aggregate functions, count and max and average, and time functions like now and current timestamp, and all those functions are available off this namespace called func. And any name you want will come out. It doesn't actually know the names of most. It knows the names of maybe 20 basic functions that it knows the type for. But you could say func.xyz, and you'll get xyz at your SQL command line. So in this case, we're calling count. We want to count the address ID rows, label them with the label count, so we can get that back in our subquery. At the same time, we want to select the user ID column, and then we want to group by the user ID. So what this subquery is going to do is it's going to select all the rows from address, group them according to each user ID, and then count the rows within each group. So basically, Jack has 2 emails, and Fred has 1. It'll be 2. Jack will be 2, and Fred will be 1. And then if we have Mary and Wendy in here, they'll get 0 and 0, I think, if I'm keeping track of my data. That's a subquery. The subquery is then its own selectable unit. It actually acts like a table. Remember the table metadata we have? It has a .c on it, and from the .c we can call upon the columns represented by the subquery, which in this case are .c.count and .c.userid. So now someone's got to be, because this is more complicated, especially because I sped through this concept in the core. Anything that you can select from in SQLAlchemy is just like has a namespace of columns on it.
Can you mix and match here with things that are core where, like, let's say you build a select statement.
Yeah.
You know, select something from Google, select something else from Google, to build a temp table.
Yeah. Yeah, that's exactly what we're doing. It's like a temp table, but it's actually called a derived table. So if then that sub queue up there actually is a core select statement. It actually is. So what happened here is the query, we did the ORM query, but then we said .subquery. It actually gives you it gives you the select that it has inside of it with an alias attached so that it gets parenthesized. So what this query is going to do is, I'll show you that in a second. We're going to get the user's name column, and then we're going to also get the count field from the subquery. I'll tell you about the coalesce in a second. And then we're going to do this by doing an outer join from the user table to the subquery. So if you just think in terms of grids of data, one grid is user IDs and numerical counts. The other grid is usernames and user IDs. We're going to outer join. So usernames and user IDs are here. And then for each user ID that has a row in the subquery, you'll get a count. And for each row where you don't have a row in the subquery, you'll get a null. But then the func coalesce will turn those nulls into 0 for us. So you get that. So that way we get Jack has 2 and Fred has 1, and then all these other people we put in have 0. And if we didn't do the coalesce, we would get a null. Let's try that to make sure. I can't even get up there, can I? Oh, there it is. Yeah, you get none instead. So the subqueue is actually an alias object. So if I print subqueue, you get that subquery, and then the alias object is a core construct that actually has, I think, element. Yeah, it is, and his select. So if I print that, that's actually the select statement, and I can keep going in. I can go into like that and see the froms ORM join. And the froms is actually on the left side. It's on the address table, and on the right side, it's on the user table. So you can. So this is how you have this statement. You can actually. It's kind of like a parse tree. Again, this is sorry. I just went really fast just now. But this is like. Yeah, when you build one of these expression constructs, it actually is a whole. Like if anyone's ever built like a parser before, you know, like if you parse an HTML into a DOM tree, right? So HTML is a big string, right? And you make a DOM. It's like this object structure representing the HTML tree. The expression language and the ORM are kind of like that, except you just type the DOM tree out directly instead of the HTML, whereas the HTML is like SQL. You just have this structure that refers to it refers to exactly how the SQL statement will be generated. That's what we got. So you can dig in if you really want to do it. You don't really have to. I have to do it all the time because I have to fix people's bugs. But generally, yeah. So anyway, the point is that when you say query, Q equals query user. It's what happened? Session query. Bleh. Session query. So Q is a query object. If I say Q to subquery, it's now this core alias construct. So we just made the jump from ORM back down to core again. And that's what I was talking about, that the core and the ORM are really together. They're really working together all the time. And the core does expose itself through the ORM. So that, what are we up to? 4:30. Wow, I go so slow. We're not going to do this because I want to show you some more stuff. So this is a run the SQL join. You know what a join is. I just showed you plenty. And this tricky bonus, it's not that tricky. Okay. Eager loading. Eager loading. So there's only 10 minutes left. Wow. Okay. Eager loading. So the n+1 problem refers to many select statements emitted when loading collections against a parent result. So if we load the user objects and then we go through each user and then print all the addresses, you will get many, many SQL statements, because for each, it'll do select star from user, and then for each user, it'll be like select addresses for this user, then select the addresses for that user, then select the addresses for this user. And you see, you get all this crap. You get basically n+1 queries. You get, if you have 5 users, you get 6 queries. The select from user plus a query for each user of the addresses. So that's called the n+1 problem. And read any anti-ORM rant, and they will talk about this. So here's how we solve that. Eager loading. Which is where you say, hey, you know what, give me the users, but I also happen to know that I want the address collections up front. So you can use a directive like subquery load, which will take care of loading all the address collections in one big query for you. So it'll do this. It'll load the user table like we just did, and then it does a second query for all the address columns, and it'll embed the original query as a subquery inside of the new one and do a join. So it does everything that we filtered for there and shoves it into a bigger query that joins to the address table to give us all the address collections in one shot. So we get 2 queries and we get the same data back because we told it up front. That's the big caveat to eager loading, is that you have to tell it up front what you want to be seeing. If we loaded some other relationship on the user, it would emit queries again. So you got to only make sure you're going to load what you're going to query. Usually that's the case. Another kind of eager loading is called a join load. Now, notice we don't do anything. We just change the command. This is really high-level stuff. We're not even telling. We say, hey, subquery load versus join load. So join load will run just one query. Join load will just do the users and the addresses in the left outer join. And this, depending on the kind of data you have, this may or may not be more or less efficient. For collections, subquery load tends to be much more efficient for various reasons that I could point you to later. And for many to ones, which I didn't show you here yet, join load tends to be the better choice. But that's kind of an extra credit topic. Eager loading does not change the result of the query. It only changes how the collections are loaded. So in this case, we're going to load the address table, join to the user entity, filter on addresses where the user related name is Jack. But then we're also going to say joined load to address.user, and that's weird because, well, we're joining twice, right? Like, why are we joining twice? Why can't we just say query address, joined load address.user, and then filter? It's because the way the join loading is working intentionally is it's going to make, again, an anonymous alias of that join so that the filter we're doing can't possibly impact the product of the join. And that's so that we can have a query and we can apply join load, subquery load as we want without the results changing. So a lot of beginners get confused. They want to join 2 tables. They use joined load because they want to load the collection and filter, which actually they don't want to do that. Well, it depends what they're doing. In this case, it actually would work, and I'll show you that in a second. But join load specifically won't do that. It's going to join twice. So we told it to load address and user. From address, join user, that's the join that we did explicitly. And then it does a left outer join again on the anonymously aliased user, and our filter deals with the explicit join, not the eager loading join. if we want to do this more efficiently, because we're dealing with a many-to-one from address to user, we happen to know that because we load address and user and get username equals Jack, we happen to know that user row is totally fine to serve as the user entity on that row. We don't need to join load again. We want address.user to be that other thing we joined from without joining twice. So we can do this thing called contains eager. This is the final variant of eager loading. So we load from the address class, join to the address.user relationship, filter them on username equals Jack, and then, hey, as you get these rows, take those user columns and stick them on the address.user attribute as well. Maybe this is simpler than what I was saying before. Does that make what I'm doing here? Is that we're going to actually filter on something on a join and also apply it to an attribute at the same time. But we're going to basically contains eager is a loading directive. It's going to tell us what to do with some of the columns that we have available to us. So you get a query that's just all the user and the address columns from address, join user, and then you get the same data back in a nice eager load. It's getting a little more weird now, right? Yeah. Yep, more weird. And I'm actually almost going to make the whole thing. We're going to have to do this, the final exam at home, but delete cascade. This is another fun thing that's good to know about. Suppose we, yeah.
How would zeros work when you have large
They will load more rows. You kind of need to be somewhat savvy of what you're eager loading. If you're trying to do, especially with the join loading, if you have like a one-to-many and each of those has a one-to-many, and you do 2 levels of join load, you're going to kill yourself because it'll return an enormous product. If you do the subquery load with each collection, it'll actually run pretty well because it loads a lot less rows per collection. It's not using an outer join anymore. I wrote a whole thing about. I can point you to the thing I wrote about it because actually it gets yeah. But yeah, eager loading. It's the whole thing that you can't just hit these commands out and expect it to just magically be amazing. It's going to be like you've got to watch the SQL. The SQL echoing also can show you the rows coming back. I'll do that a lot. Like if you have a query that's not joining on every column and you're getting a huge product and you're wondering why your query is so slow, you might want to see the rows and like, whoa, all these rows coming back that are being deduped because the ORM will actually dedupe the rows and you might not realize you're getting millions of rows and actually deduping them all. So things like that. It doesn't save you for being savvy about SQL. It just automates the task of writing redundant SQL. Like you know what you want to do. It has a bunch of recipes cooked into it. It just automates doing them. But you can't be ignorant of how it works. You got to really, you know the SQL. It's for people. It was an ORM for people that hated ORMs. That's what it was. I like ORMs now because I wrote one. So, So anyway, I just want to share this cascade thing because it's kind of important to know. If we load Jack and we want to remove one of Jack's addresses and then we commit that, what will happen is it'll update the foreign key to be null. Now, we might want to instead have that row be deleted because the addresses are kind of only local to the Jack user. So we can do this thing, because remember before we talked about save update cascades, where if you put the user in, all the addresses cascade in, it follows the pattern. It follows along the relationship to load the addresses in. We can do it with deletes too. We can set this thing called cascade. Now normally this would be set when we create the relationship directly. I'm setting it here just so that I have to rebuild all the mappings from scratch. You can set it. This is actually a brand new feature to do it this way, just for tutorials because I always teach it this way. We can say to the user addresses property, hey, I want you to delete all the orphans. Meaning if an address is removed and is no longer referred to by any user, delete it. So if we do the same operation now, we load another user and remove the address row from Fred and commit it, it'll now delete that row instead after it does its refresh. That's another aspect to controlling how the unit of work does its work. Because really the relationship is so much happens in that linkage between classes. It's really where most of the complexity of the ORM is the way you mediate between 2 tables and 2 objects. There's just so much that goes on there. It's pretty crazy. If we delete the user itself, that will also delete all of the address objects. This is also something that you can do in your database using on-delete cascade, which is a database directive that will do the same thing. And with SQLAlchemy, you probably should use the on-delete cascade directives if you want them because they are more efficient. When you do an operation like this, SQLAlchemy has to load the rows in and delete them individually. Whereas if you do the delete cascade on your foreign key, your database will do it automatically. And you can tell SQLAlchemy that, hey, this foreign key has cascade on it, so you don't have to load the rows in. They'll be deleted for you. So that's kind of something that you could explore later. It's in the docs about on-delete cascade. And again, you know, it's not automatic. You have to tell it, because some databases don't support on-delete cascade, like Oracle, which is really shocking, but it's quite inconvenient. So that's another thing to have in mind. And then, oh yeah, I could tell the next slide is the final exam. Is there someone here that knows about the tutorial survey you're supposed to fill out? Can someone? There's supposed to be a survey that I was told, and no one. Yeah. So I think I'm supposed to have people fill that out now, because they're saying that if we don't have you do it now, then you won't do it. So is it a link? Oh, is it a link? It's a link. Now, how do I show this to people? Type it in. Yeah. HTTPS. Yeah, that's not on. Oh, the Google. Well, too late. PyCon 2013 tutorials. Or HTTPS Google PVHDC. Yeah. Nothing happens. Yeah, let me do this up. And then this last slide, if you've all got it on your computer, is the final exam, which is to build a you know, a nice little model and do some fun queries. It's a fun exercise, and you can email it to me. This, you shall do that. It's kind of like, yeah, you can do this. You know, it's probably a good idea to do this. So what happens is all the DB APIs all have their own little quirky things. You know, there are, most annoyingly, 6 different formats for using bound parameters, which is really annoying because you only need 2. So what this code is, and I know that how far can people see almost to the bottom? You don't have to see the whole thing. It's just if you can see maybe to this part, you know, you'll get the nutshell. So when you work, so this is an example of code using a database API known as PsychoPG2. Which is an adapter for the Postgres database. And this is what it looks like. You make a connection. You connect, give it a username, password, and some information about where your database is, maybe a host name, which is not here. And then when you want to actually do something with results, you need to make a cursor. You say connection.cursor, and then we can use the cursor to execute some SQL. So we're doing a select from a table here. And that little imp ID symbol is a bound parameter, which means it's going to replace that number 5 into the statement. But we let the driver do that because different databases have different ways of substituting parameters. And a lot of you have probably heard about something called SQL injection attacks, which is when you see this a lot in like PHP applications where they'll write a SQL statement where it's like, you're logging into a website, and it'll be like select star from user table where password equals, and it'll be like quotes and a string concatenation. And then someone will go onto the website and type a bunch of SQL in the password box with some semicolons so that they will inject a whole new statement into the statement and then delete the guy's user table, something like that. So that's SQL, and there's a lot of websites being hacked, and it's always through this program called WordPress. So you know, because they don't have a consistent pattern. So we want to use this bound parameter thing, and it really is this whole, I feel like it's a whole subject because people always don't seem to know it fully. Postgres actually is going to substitute that number 5 into the string and make sure it's properly quoted, and then it'll send it to the database. But if you talk to a database like Oracle, and you use a database API called CX Oracle, it actually never does the interpolation at all in Python. It all gets sent back to the server, and the Oracle server actually deals with the separate parameters. So you can't assume you know where that number 5 is going to go. So we keep it separate, and it's not just about string formatting. It's also about interpreting different data types like dates or Booleans or large decimal values in the way that the backend wants. So when we talk to a relational database, we want to, as much as is humanly possible, to substitute all literal values, numbers, names, dates, any kind of nouns that represent data in the database. Not the structure of the statement, not the names of columns, not the names of tables, but the data that might be inside of a column or in an expression. We always want to have that escaped out. So when we use SQLAlchemy, it's going to make it actually kind of difficult to not do that. One of the big things SQLAlchemy will give you is you almost never have to worry about making sure literals are bound parameters. Checking my time, good. So the DB API I thought was a little bit verbose that first you connect, but you can't just execute from the connection. You have to make a cursor. And then the cursor represents where you get the results from. And that is the traditional database approach. I thought it was a little bit verbose. So the engine's going to try to make this a little less verbose. So important facts about the database API is that when we just saw that connection just now, this is the one area that the DB API PEP 249 is fairly strict, is that the connection must be in a transaction. So if you connect to a database with DB API and you start running insert, update, delete statements, by definition, they will not be committed to the database until you call the commit method on the connection. And that is basically the opposite of what we call auto commit. It's basically not auto commit. It's always the pending thing. The only exception to that is if you're using MySQL with the MyISAM database engine, which doesn't have transactions. So it's providing the database you have, which almost all of them support transactions, you will not be in auto commit by default. And database API, a lot of them do have an auto commit mode, but it's not a standard part of the spec. So SQLAlchemy does not build upon a database API level auto commit. It actually has its own auto commit, which we actually don't even use that often. So I'll show you that later. So as I just went through, the DB API encourages bound parameters via the execute and execute many methods, but it has 6 different actual string formats for that string I showed you. There's other formats that we'll have to deal with before we actually use SQLAlchemy. All DB APIs have inconsistencies regarding data types, primary key generation, custom database features, result cursor behavior, all kinds of stuff. It's really more varied than anyone could imagine. And I know there's a bullet that's too low for people, but won't be too many. DB API has its own exception hierarchy, which SQLAlchemy exposes directly. Meaning if you try to connect with database API and the connection fails, it'll throw interface error or something like that. And if you try to do a statement that inserts a row with the same primary key, you'll get a integrity error. And these are errors that are defined by the database API. SQLAlchemy has its own version of those exceptions that it will wrap. And I don't want to go too far into that detail because it's kind of a minutiae detail. I don't know why I put it in the slide, but it's something to know. So SQLAlchemy, so far we're just doing the Python database. We're doing other things that already exist before SQLAlchemy. So the first layer in SQLAlchemy is known as the engine, which is the object that maintains the classical DB API interaction. The thing I just showed you was the classical DB API interaction. And with that, I would show you this. I would go to the first Python scripty thing, which means that for those of you who managed to get the thing installed, we would run the slide REPL command. Who's got slide REPL going? How many people have it going? Okay. So we do have some helpers if people want to. Is Ben? You're here, and Ben. Yeah. So if people want, does anybody want help while we're talking to get the slide installer? Anyone who doesn't? Okay. We have helpers in the back, and raise your hand, and they'll come by and try to help. So I'm going to run it with this flag -- pres, which will make it clear the screen, and you can do that too if you want. And if you don't run with the -- pres flag, it will just kind of roll down the screen, which might be easier for you to scroll up and see what's happened. So, and then I just started up, and the first thing it did, I didn't really start it yet. It ran a bunch of SQL just to kind of set up the very quick examples we're going to do for the engine. So the first slide is actually this. So here's the first slide. So, right, okay. So this is legible. The letters are big enough, and okay. So this is what it looks like. So now we're in Python, and we're going to actually do something with SQLAlchemy. We're going to create an engine. And it's the function we use is aptly called create engine. So we import the function, and then we say engine equals create engine, and then we pass it a URL. I'll show you some examples. And so what this URL is doing is it's creating a SQLite database called sum.db. It's creating it in the local file system. If we wanted to make a SQLite database at an absolute path, we would actually use 4 slashes. That's how it would look. Just kind of a historical detail. If we wanted to connect to Postgres, the URL would look more like this. If I could type. This is the URL I type every day when people email me Postgres questions. I have this little test database that I use. So the normal format is the first part of the URL is kind of this keyword that identifies the kind of database you're going to talk to, and there's a default dialect. If you wanted to specifically talk with the PsychoPG2 database API, which is the default, you could say that. You could say that, Postgres for PsychoPG2. Then you have username, password, at, hostname, / database name. Only SQLite, which doesn't use a host. SQLite it uses just local files. It doesn't use a server. So you just give it a file name. So SQLite is what we're doing here because most people here have SQLite installed as part of your Python build. And it's pretty easy to work with for demonstration purposes. So we have this engine object. And there it is, all right? And it's a Python object. It hasn't actually connected to the database. All it knows is this URL we've given it, and it won't do anything until we tell it to run some SQL or to connect. And then it'll suddenly be like, oh, I got to go to this URL somewhere. I got to figure out what I'm going to do. So the next slide should show that. So this next slide is just showing the most handy convenience method of the engine is just a method called execute, where you pass it a string, and that string goes straight to the database API as is. This is probably not, you probably don't remember this, but when I showed the DB API example with PsychoPG2 earlier, there was a bound parameter which used the Python format with the %sign and parentheses and an S, and now this SQLite uses the name format. Because we're not at the level yet where SQLAlchemy is trying to help us with the bound parameters. This is just the low level, the engine's going to run a statement through the database. Historically, database abstraction and ORMs, when you do that, kind of an old-fashioned approach is to kind of distill each database backend down to its, the lowest common denominator of all those backends. So if they all can do a select, then that's all that your thing can do. And if Postgres has, window functions, but SQLite doesn't, well, your ORM won't have window functions. Things like that. So SQLAlchemy is trying. Everything about SQLAlchemy is kind of a middle ground. There's nothing. We're not all anything. We're middle ground all the way. Just try to walk that line between where we don't want to write completely different code for every database, but we want to still be able to do some things that are database specific. And it actually has a lot of techniques nowadays to really, like if 2 different databases do something totally differently, you can write your own little adapter that does the thing you need to do for both backends, and it'll look pretty transparent. So it's pretty cool for automating the work of talking to a relational database. It's a tool for automation. So it never hides the database or its concepts. Developers have to continue to know and think in SQL. The best way to write a SQLAlchemy query is to just know what the SQL query in your head would be, and you pretty much can write it in SQLAlchemy's language fairly straightforward once you're good at it. But instead of trying to hide anything, it just provides automation of the concept of talking to the database and DRI, which is don't repeat yourself. So the concept of don't repeat yourself, I like to say that a good application is maybe 80% dry, meaning if you have an application that's 100% dry, like nothing is repeated anywhere, it tends to be really rigid. Like if you need to add something new to your app, everything doesn't fit into your big giant system. So I say 80% dry, so there's a little bit of wiggle room for things. You don't quite. There's a little bit of repetition here and there, so that there's some flexibility. So SQLAlchemy is designed to help you to write the best database interaction layer that you can for your application. So it's really it's not a casual dip in the pool. It's kind of you need to get into what its philosophy is the best way to work with it. Allows expression of database and SQL tasks using declarative patterns. That's more of the ORM, and we'll see what that looks like after the break, actually, which will be the ORM. So I should say basically the way we're going to, well, I'll show that in a second. This is an overview of SQLAlchemy. This picture is on the website. If you go to the documentation, there's an introduction page. And this is the same picture we've been showing for years. This is kind of a overall architectural view of what SQLAlchemy is. So, you start with your database. The cylinder symbol is the universal symbol for database. And then when you have your Python installed running on your SQLite library running, that's called the Python Database API, like PsychoPG2 for Postgres is a DB API, MySQL for Python. So we're not at SQLAlchemy yet. Then you go here. OK, so SQLAlchemy has this first layer called the dialect, which is code that knows the special things about your database API and the special things about your database. Connection pooling is kind of an optional but usually used feature that will maintain some connections so you can reconnect really quickly. And then those are revealed through an object called the engine, which we're going to see in a minute. So the engine is the most core unit of connecting to a database with SQLAlchemy. And then along with the engine are these components of the SQL expression language, which we're going to do as a whole section, and the schema representation library, which is also a whole section. And then all of that is part of a big thing called the SQLAlchemy Core. And none of this has anything to do with object relational mapping whatsoever. So when you say using the SQLAlchemy, you could be totally here, and you're not using an ORM at all. You're using just the SQLAlchemy Core. And that's what a lot of people use. If you go to Reddit, Reddit uses their really super custom thing built on Core. Now, ORM is a whole other thing. It's a whole topic of its own, and that builds on top of the Core. So the ORM doesn't talk to the database directly. It goes through SQLAlchemy's Core APIs to do what it does. Any curiosity, questions so far? Or any? OK. Well, what I can do, actually, this one here. I'll show you this slide, but most of the slides are not really going to be that low. Most of the stuff will be in the slide runner, so we shouldn't have too much of a problem. That's the bottom, if you can see it. Don't worry, we're not going to be in the slides for most of the thing. Some of it. So the core, here's the rundown I just basically gave. The engine is a registry which provides connectivity to a particular database server. The reason it's a registry means it's kind of this object in a computer or an application that just stores some common repository of information about something. In this case, the engine stores information about the database that it's just connected to. The dialect is kind of this thing you don't see directly usually. It's within the engine. It interprets generic SQL and database commands in terms of a specific database API and the database backend, so it knows how to produce a query that MySQL will like versus a query that Oracle will like. Connection pool holds the connection of database connections in memory for fast reuse. And there was recently a big flame war on Hacker News about PG Bouncer and how connection pools are terrible. But I still think they're fairly handy for general use. The SQL expression language allows SQL statements to be written using Python expressions, and we'll see a lot of that. And then the schema and type system uses Python objects to represent tables, columns, and data types. So that's what's in the core. And the ORM, what's the job of the ORM? The ORM allows construction of Python objects which can be mapped to relational database tables. We'll see a lot of that. It can transparently persist objects into like the state of a Python object, into a database table using a pattern called the unit of work pattern. And that's all coming up. It provides a query system which loads objects and attributes using SQL generated from those mappings. And it builds on top of the core. So all the SQL that the ORM generates is generated via the core. And this diagram I actually got from someone else. This is plagiarism. A guy that ran a tutorial for PyOhio had this idea that SQLAlchemy is like an onion. And I thought that was a great idea. Because it really is like this, that you start, and the way when I wrote SQLAlchemy, I started this way. First I wrote this engine thing that knew how to emit SQL with the Python database API in a way that I liked. And then I wrote the system that talks about how tables in a database can be defined in Python objects. Then I wrote SQL expressions, and then object relational mapping was kind of on top of all that. So it's like an onion, and you can learn it from the inside out or the outside in. And I've kind of flip-flopped over the years as to should I teach the ORM first and show some quick success and then get into how it works later, or the other way from the inside. So this particular talk, which I have in the intro on the website, so I'm sure you saw it, we're going to go from the inside out, which I think will be better because the engine stuff should be pretty simple. The metadata stuff should be fairly enlightening. The SQL expression stuff we're going to take until the break. And then no matter how far or not far we get by the break, after the break we'll do all object relational mapping after the break. Because really, when you use SQLAlchemy, we're normally using the ORM all the time, but we know about these other things. We know about these other concepts at the same time. The most confused users that I get on the mailing list are those who know the ORM, they know what it's doing, but they have no idea what an engine is. Those are the people who need, now they can learn new ORM patterns, but I have a really hard time explaining to them, well, there's this engine and it's kind of in the middle because they don't have that concept. So I'd like to get the concept across. And then as far as learning how to do fancy ORM stuff, hopefully you can go forth and, get more stuff. So this is the basic stuff. So there's also a color, I like to use color coding. So we have green, assuming everyone can see those colors as distinct, because some people can't see color. Green, blue, and orange, and red. So we'll see, so we start with level green, which is the engine, and right on time. So, okay, so with the engine, we start with what the engine, the job of the engine is to deal with this thing called the Python Database API. And that is a Python PEP. You guys know what a PEP is, a Python Enhancement Proposal. So basically everything that Python does, anytime they want to add a new feature, they make this thing called a PEP. And there's a whole website of all the PEPs. And basically all the features come out as all the APIs, and the WSGI API and the style guide are all PEP. So PEP 249 is the Python Database API. And it's the de facto system for providing Python database interfaces. There are a few packages for talking to database that don't use the DB API, but they are few and far between. There are many DB API implementations available, and most databases have more than one. For MySQL, there's at least 7 or 8 DB APIs you can use. And then the features and the performance and the stability and the quirks and maintenance and everything varies wildly. DB APIs, for as good a job as PEP 249 attempts to do to define consistent behavior, it has a lot of like, this is suggested, and it's suggested that APIs do this, and most APIs will want, it doesn't say, you shall do this. Right, so, and then we were asked to give you some updates. The break is at 2:50, so if I'm just talking, everyone just tell me break time in case I lose track. There are on-site volunteering opportunities for PyCon, swag bagging from 4 to 8 p.m. I think you just show up and put stuff in bags. They need help at the registration desk. And there's a web page, there's 2 web pages that have information about volunteering for PyCon. In case you want to write that down. Okay. And then we have the prerequisites. And then we go with the relational database reviews. So what I should do is get an idea of people's Python experience level using Python for less than a year. Okay, we're using Python between 1 and 3 years, between 3 and 5 years. Okay, over 5 years. So we see that's how it goes. We have every demographic represented. So I am absolutely positively sure to let someone down because it'll either be too easy or too hard. So assuming someone's going to blog how the talk was either too easy or too hard, if you like the talk, blog about that also. So there's a counterpoint to the guy who's going to complain that it was too easy or too hard. Are there any questions from the people that did the handout, like about some of the relational database stuff? Did I get anything wrong? Or, we're all good with what was in the handout. We covered tables and columns and data definition language, DDL, and inserts and updates and deletes, and then we're all pretty cool with the general idea and selects. Am I going too fast? Joins. Grouping, we're not really going to do grouping in the thing. Well, there's a little bit of grouping. It's not that critical for this tutorial. Overview of acid, atomicity, ISO, and then there. Great. Okay, and no, also, who has used SQLAlchemy before? Like, okay, who actually uses it for work and actually deals with it every day and wants to just learn more about its basic fundamentals? Who's absolutely no idea SQLAlchemy? Okay, okay, who uses Django ORM? Maybe. Okay, all right. So it seems like most people here have used some kind of relational database abstraction layer, and you're okay. That'll help. So SQLAlchemy is the database toolkit for Python. That's our tagline. It was introduced in 2005, and it presents an end-to-end system for working with the Python DB API, and I'll show you what that is in a little bit, and relational databases and the SQL language. And the current release is 0.8.0, which I just put out this weekend. And we're very close to where I'm going to call it 1.0. I'm not totally sure yet, but I might just go from 0.8 and just kind of jump to 1.0 kind of quickly, because it really is kind of time to be 1.0. It's only been 7 years or whatever. So the goals of SQLAlchemy, it's to provide code helpers, tools, components, APIs, what have you, to assist with the database development at every level. Provides a consistent facade over the Python database API. Provides an industrial strength but optional object relational mapper, or ORM. And it can act as the foundation for any number of third-party or in-house tools. If you do a search on PyPy for SQLAlchemy, obviously there's dozens of packages that are built on top of SQLAlchemy to provide different kinds of relational patterns and fun things. We're going fast, actually. Okay. So philosophies of SQLAlchemy. The philosophy of SQLAlchemy is bring the usage of different databases and adapters, database DB APIs, to as consistent of an interface as possible. So basically, all the world of databases, we have MySQL and Postgres and SQLite and Oracle and Sybase and Microsoft SQL Server and Informix and DB2 and everything else. They every single one of them has completely different stuff going on. Like they all have the select star from table. Everyone's got that, but they are so different in so many ways. And SQLAlchemy is still going to expose those distinct features and behaviors, but it's going to try to find this middle ground between where we can kind of have some consistency between these platforms, but at the same time not lose the ability to take advantage of what each platform offers, which is a tricky thing, because usually,